to this to this potential, we find that there is a column 1. There is here we have the column 1, and we have also the cornel term, which is BR, and also harmonic term, which is CR squared. So it is melting between the column potential and the harmonic oscillator. We all know that this term BR can be put into the harmonic term by using just a change of variables. But this potential, we find also this potential when we study Sharmarian robotomium. There is a mistake here. It's botonium, not bitomium. Okay. So now we will start to how to solve this potential. We will use the Frobenius method, which is a general method to solve differential equations. So we will write the solution as a polynomial, and then put this solution into the radial Schrödinger equation, like you see. And we have this parameter. Just to reduce the equation, we write these parameters. If we look to the equation 25, we have the column term, the cornel term, the harmonic oscillator term, and the centrifugal term. We write the solution as done by Hahn in his first study of this equation, and also I think by Skolan. So this is the ansatz. So when we put this solution into the equation 25, we get this one. Because alpha F and beta F are free parameters, we choose the parameters to reduce the equation to the following form. These two conditions, 28 and 29. So we get, so this, the equation becomes, as we can see in 32. This equation is the biconfluent Hahn equation. For the biconfluent, to get the solution for the biconfluent Hahn equation, we must use the Frobenius method, the polynomial writing of the solution, and what we get is this recurrence conditions. The difference between it looks like when the recurrence condition for the hypergeometric function, but there is a main difference because here we have a 3-term recurrence solution, not a 2-term. So to cut off the polynomial, so the all solutions will be how do we say convergent, not divergent, because all the Schrödinger equation must be convergent. So to get the solution for the solution to be convergent, what we have to do is to cut the polynomial. How to cut the polynomial? We have to get an plus 2 equal to 0 and an plus 1 equal to 0. So all the remaining parameters over an plus 1 will be all zeros. How to do so? We have to write, there is 2 conditions. So we have the parameter multiplied by an must be equal to 0, and the an plus 1 must be equal to 0. I have to say that all the works dealing with the biconfluent differential equation use only one condition which is that the parameter of the an is equal to 0. Here in our work, we are working with the 2 conditions, which are the parameter of an and also an plus 1. If we use these 2 conditions, this is the energies of the system. And we see here, in the this is for the case n equal to 0. Because we don't write the energy for the case n equal to 1 because they are too heavy to write. But for and here I have to mention that the L number, it is not like in the hydrogen atom. It is free parameter. So it is integer, and he can takes all the value from 0 to infinity. So here in this expression we have an infinity of bound energies, and we can see clearly here that we have the harmonic term, which is the first term, and also the Colombian term, which is the second term. And this is the new result, because all the works before us that works on the Killing-Back potential, and when they use only the condition that the coefficient multiplying an is equal to 0 without the condition that an plus 1 equal to 0, they only find the harmonic oscillator term, not the Coulomb term. So here, when we use the two condition, we have found that there is the harmonic oscillator term and also the Coulombic term. So we have the C, which comes in the potential with the harmonic term, and the A, which comes in the potential with the Colombian term. What is the B? The B is absorbed into the C. It's absorbed here because we know that when we have an harmonic potential, which is AX2 plus BX, we can absorb the B into the harmonic term with the change of variables. So here we have found all affinity of bound states, and also we can the eigenfunctions are written here like this, which where HB are the hand polynomials or the hand function if you want. So we are the work is we are still working on this this system, because we are trying to simplify the expression of the energies when n equal to 1, because they are too heavy to write, but we are trying to simplify it. I think so. It was done just I think 2 days or 3 days ago. We have found a way to simplify it. For n equal to 2, we don't know how to write it. We write it, but it's very, very, very heavy to write, and we don't know how to simplify it. I hope we will do this later. So this is we are just beginning with this work. So we find the bound states and the eigenfunction, and now we have to apply this to real systems, and using the experimental values of parameter to justify our study. This is just a small overview of our work on these systems, which are the confined atomic systems in plasma physics. Thank you for your attention. If you have any question or comments, I will welcome it.
Thank you for a very nice talk. Are there any questions for the author? I wanted to go back to the slide where you said an plus 2.
Yes.
So an 2 plus has to equal 0, right? You want to cut the series, right?
Yes. Yes. We want to cut the series. Yes.
So an 2 plus 0 if an plus 1 is 0.
So we have two conditions. In equation 47.
Yeah. And the coefficient of an is 0.
Yes.
All right. So now 0 equals 0. That's what you're basically coming to, right?
If we use only the coefficient of an equal to 0, we will find the energies. We will find the harmonic term, but we will find plus b square over 4c.
Okay.
B square over 4c.
So that is. Can you go back one slide?
Yes.
So this that sets conditions on these coefficients, right? The beta n plus 2.
So if we put the coefficient of a n equal to 0, we have to put this one equal to 0.
Right.
This one,
yeah,
it gives us the energies, but it gives us only the harmonic term, not the Colombian term.
Gotcha. Okay. All right. Yeah, I guess
to get the Colombian term, we have to use the second condition, which is a n plus 1 equal to 0.
Yeah.
And you have to write a n plus 1 according to all the previous parameter. For n equal to 0, it gives us a1 equal to 0. For a1 equal to 0, we get this one. We get the term minus mu a square over t h bar l plus 1 squared, which is the Colombian term.
For n equals 0 only.
Yes. For n equal to 1, we get it's heavy, but we simplified just 2 or 3 days before. We can write it here. You will find here l plus 1 squared multiplied by l plus 2 squared, and there is a square root where plus and minus and square root.
Right.
This is for n equal to 1, but for n equal to 0, this is the bound states, the bound energies. These are the bound energies.
And so is the method not valid when you go to unbound states? Or does it not describe unbound states very well?
Can you repeat the question?
Can this method describe unbound states or ionized states?
Yes, okay. It can. But we have to make how can I say, because the quantum numbers here for the Killing-Back potential, for the Helmholtz equation for the Killing-Back potential, the quantum numbers are not the same as the harmonic oscillator or the Coulomb potential, and we are trying to use experimental data to make the correspondence between the 0 states here and the 1s in experiments, and the 0 1 here, and I don't know, perhaps the 2s and the 0 3. What is the 0 3 in our work? What is the level correspondent to 0 3 in our work according to the experiments, and so on.
Gotcha. Okay. All right. Thank you.
You're welcome.
Thank you. Are there any more questions for the author? If not, then let's do a clap and give them a thumbs up.
Okay.
And then I do not see Tepper Gill here. Tepper is in the United States, and so it is 3 a.m. in the United States.
3 a.m. Yes.
So maybe not available. Is there a Rosemary Ashun? That talk. I don't see that person either. Is there a Sharaf? Said. Stephen Wandel? No. Rick Tribino, you are here. Rick?
Yes, Rick's here. Yeah. Did you want Rick to present? I can go get him. Yes, it is 3:30 in the morning, but we're here and awake.
Well, you can either start now or you can wait until his time comes up. But there seems to be some no-shows here.
Yeah, what do you prefer? If someone logs in live, they might want to log in at 11:45.
I prefer to wait to his time.
Wait to his time is perfect. We will wait.
Okay.
We will see you at 11:45 your time, 3:45 our time.
Correct. Okay, great.
Thank you.
Bye-bye. Hello, Trevor. So still no Tepper Gill? Tepper not here? Okay. Rosemary Ishun still not here. Is Sharaf bin Kadbi here? Saraf still not here. I see Rosemary Ashun, you have just arrived. Rosemary?
Hello.
Hello.
Yes, sir.
You have arrived to give your talk? Is that right?
Okay. I thought I'll be there.
Say again?
I thought my presentation
If you want to give your
at
talk, you can start.
11:45. I thought it would be at 11:45.
Your talk was supposed to be at 10:45.
10:45. Yes, please.
Which was actually an hour ago.
Really?
Yeah.
Okay.
But you can start now. We have a slot availability for you to start right now.
Okay.
Can you
And
share
I'm
your
ready to
screen and
go.
start?
Yes, please.
Okay.
So I'm trying to share my screen.
Try it now.
Oh. Hello.
Yes,
Please, can you see my screen?
I cannot.
Um, I saved it in PowerPoint, but it's telling me I should save it in PDF. So I'm trying to save it and
You're
share
trying
it.
to do what now?
I'm trying to share it and it's not responding, so I'm still on it.
Okay, keep trying.
Okay. Hmm. Oh,
I could chat.
the thing is failing. This is serious.
Do you see at the bottom of the screen where the little green button where you can share your screen?
I see it, but my presentation is in PowerPoint and it's telling me to present in PDF form.
Are you trying to save it or present it?
Okay, I'm on it.
Actually, why don't you hit the little green button and I can help you. The green button that's
Okay.
down at the bottom. Okay, here we go. Oh, wait, that's not you.
Talk.
This is Rick. I put mine on, but my time is approaching, and maybe I could do my talk while Rosemary figures out the screen sharing issue.
Yeah, that works.
Okay.
Okay, can you see my
Okay.
screen?
I can see your screen, yes.
Excellent. Okay.
And okay, go ahead.
All right.
The School of Physics at Georgia Tech has kindly allowed me to teach optics over 20 times, and I chose to obsessively improve my PowerPoint lectures every year. I've created over 24 full-length lectures with thousands of animations and photographs, and I've also taken heavy advantage of image and video content uploaded to the internet by others. I've even carefully written narration scripts and painstakingly recorded narration for them during the pandemic. They're now essentially complete. I also share them on my website, frog.gutech.edu, resulting in their use by lecturers and students worldwide, even before I narrated them. And lecturers and students also routinely provide feedback to improve them. Assistant professors are the most appreciative. These lectures save them hundreds of hours of lecture preparation time during a period in their lives when time is in short supply. I've also created an analogous narrated modern physics course. It's particularly enjoyable, I believe, because I teach it historically, and its cast of colorful characters adds greatly to the fun. These two icons link to the two courses' lecture files, which can all be downloaded. Let me show you a few slides from these lectures. Here's a photograph I took to illustrate a small depth of field. Technical drawings are easy in PowerPoint, and here's my drawing of the sun illuminating the Earth and the resulting atmospheric light scattering. Here are two more photographs to illustrate atmospheric polarization effects due to light scattering. And another I took to inspire the study of nonlinear optics. But motion is much more exciting. So here are some electronic and molecular vibrations. And electromagnetic waves propagate. An animation of one is worth 1,000-word hand-waving explanation. And stimulated emission and its chain reaction in a laser are also better illustrated using animation. And here's a simple illustration of Boltzmann population factors for a high and a low temperature. Derivations are much easier to present when diagrams, labels, variables, equations, and cancellations pop up precisely when you need them. Here's my derivation of Snell's law, significantly sped up here because you won't be tested on it. And my derivation of the ray matrix for a curved mirror, also significantly sped up. Describing absorption, spontaneous emission, and stimulated emission is much easier with an animated graphic. And the Doppler effect becomes obvious with a little animation. Explaining how a laser can use a saturable absorber to generate ultrashort laser pulses benefits from animations like this. Now, as I mentioned, I haven't created all the content by myself. I've also used images and GIFs from the internet, and most such uses satisfy all 4 of the conditions of the fair use doctrine. The internet is full of beautiful images for educational purposes. Here are amazing illustrations of strain induced by refringence, and pulsed light beams crossing at an angle, yielding irradiance fringes. And describing Isaac Newton's views of whether light was a particle or a wave is much more illustrative with these GIFs. And here are images of interference from 2 point sources emitting spherical waves. It's easy to see that the fringes are an angle and are farther apart when the sources are closer to each other. And circular polarization is a difficult concept to explain or draw on a blackboard. A video is really necessary. And don't even try to explain an optical vortex in only words. Explaining what incoherent white light really looks like is also tough, but this speckle pattern happens to be what spatially incoherent monochromatic light looks like on a microscale, and this colorful movie shows what light bulb light looks like with ultrafast temporal resolution. And to explain special relativistic velocity addition, animations really help, especially as the Enterprise is destroyed. But fortunately, that's only when the velocity addition is Galilean. Relativistically, it survives to seek out new worlds and go where no one has gone before. And explaining Lorentz contraction is vastly simplified with cute graphics like this. Same for this beautiful movie of a quasar, without which a discussion of cosmology just wouldn't be satisfying. Want to hear the first few minutes of my modern physics course? The story of modern physics may well be one of the greatest stories ever told. It has as many twists and turns as a theatrical murder mystery, and some of the twists are so mind-bending that you won't believe them when you first encounter them. And whether we're talking about the physics or the physicists, it has a diverse cast of fascinating and colorful characters. Like theater, it begins innocently enough, with everything apparently under control and everyone happy. Then numerous cracks in this blissful state of affairs begin to emerge. Complex subplots abound. Players encounter crisis after crisis, with things often looking quite bleak. But in the end, a wonderful resolution emerges, comprising a completely different picture, with numerous victims falling by the wayside and new heroes emerging to save the day. It even ends with hints of a sequel. Of course, the sequel hasn't been written yet, and perhaps some of you will play a role in it when it is. And most importantly, unlike theater, it's all true. This course won't just be about modern physics. It'll also tell the story of modern physics, that is, its history. It'll begin in the mid to late 19th century. It was a time when physicists blissfully thought they had everything figured out. Indeed, American physicist Albert Michelson wrote in 1894 that the more important fundamental laws and facts of physical science have all been discovered. And these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. Our future discoveries must be looked for in the 6th place of decimals. Ironically, it was Michelson himself who a few years earlier had discovered one of the first great cracks in the foundations of the physics of the time that led to the chaos that ensued. And British physicist Lord Kelvin wrote in 1900 that there's nothing new to be discovered in physics now. All that remains is more and more precise measurement. Physicists had the apparently rock-solid work of Isaac Newton, which described the motion of all bodies. In addition, Lord Kelvin had performed exacting experiments to determine the behavior of gases. And physicists of that time even had an excellent grasp of waves, although waves were more often considered a fringe subject than a fundamental quantity. The fundamental entities of the universe were particles, and waves, such as sound, were simply collective motions of them. Conservation of energy, linear momentum, angular momentum, and charge had been discovered and provided spectacular insight into the laws of motion and thermodynamics. And thermodynamics had firmly established the atomic theory of matter. Only a few minor issues remained to be ironed out, such as the precise nature of atoms and light, and some odd electromagnetic phenomena, and a correct formula for the spectrum of hot objects, which had proven frustratingly elusive. In hindsight, we can rightfully state, oh, how very wrong they were. Although they didn't realize it, they were about to experience the greatest scientific adventure of all time. How about the first few minutes of my optics course? Light is amazing, and humankind has been justifiably fascinated by it from the time our species became sentient. Let there be light was the Judeo-Christian deity's first and most important task. Hindus worship light as divine and omniscient, and their festival of Diwali symbolizes the victory of light over darkness, knowledge over ignorance, good over evil, and right over wrong. Festivals of light are also celebrated by many other cultures, and here's a photograph of a beautiful one at the Cincinnati Zoo and Botanical Garden. Nearly everywhere in the world, light is the symbol of joy and life-giving power. Indeed, a person is a great joy if he or she is the light of one's life. A charming person is said to light up a room. A wise person is a guiding light. And when we're finally making progress, we can see the light at the end of the tunnel. A good idea is symbolized by a light bulb over one's head. And we often shed some light on a subject to become more enlightened and eventually see the light. From the moment we awaken in the morning until the moment we fall asleep at night, light is our main tool for understanding and interacting with the world around us. And with the use of optical devices like microscopes and telescopes, light has given us the entire fields of biology and astronomy. Light was responsible for the great revolutions in physics in the early 20th century, quantum mechanics and special relativity, and it plays a key role in general relativity as well. Even today, in ongoing tests of the fundamental nature of physics and reality in general, light is the key element. Light is also practical. It's at the heart of the great technological revolutions occurring now in telecommunications, geopositioning, weather forecasting, and medical and military imaging. In this course, we'll talk about all aspects of light. We'll begin by asking simply, what is it? Is it a particle or a wave? Or somehow both? This debate has continued for centuries, and although our understanding of it has increased drastically, we're still refining our precise answer to this question. But we can definitively answer many important questions, and their answers provide answers to many other long-standing questions. They include, how does light interact with matter? How does it interact or interfere with itself? And why do things look the way they do? What gives an object its color? How do prisms disperse light into its many colors? Why is the sky blue and clouds white? Why is water in some cases clear and in others blue? Why are some surfaces shiny and others not? Why do windows look like mirrors at night? We'll answer all of these questions in this course. We'll also resolve some 19th century dilemmas and talk about lasers and the many ways they're different from light bulbs. And we'll talk about rainbows, sunsets, polarized sunglasses, cameras, concert holograms, mirages, and butterfly iridescence. In short, we'll not only develop a detailed understanding of light, but we'll also use this understanding to explain a wide range of optical phenomena and answer many questions you may already have about the world and its appearance, and many you perhaps haven't thought to ask. In this first lecture, I'll provide you with a brief history of optics, and I'll outline in more detail precisely what we'll cover in this course. How well have they worked in practice? Well, it's too early to be definitive, but remarkably, they completely solved one pesky universal problem immediately: the ubiquitous exponential decay of college class attendance over the semester. Indeed, in my optics course last fall, because they could watch them anytime they liked, All the students reported watching nearly 100% of the lectures, likely a world's record for voluntary class attendance in a semester. One student actually binge-watched all the lectures and finished the entire 15-week course in just 6 weeks, and she achieved a grade of 98%. Also, subjectively, the students reported greatly enjoying them. Finally, grades have been spectacular, mostly A's, for the first time in a course of mine. By the way, this was during the peak of the pandemic, when student grades generally fell significantly elsewhere. So I believe that this approach is working very well so far, despite the fact that my lectures remain works in progress.
Very nice.
Thank you.
Are there any questions for the author? Anyone who was here? Can I ask? So let me just get a quick question in. And what level is it? Is it undergraduate optics or graduate optics?
Undergraduate optics. It's a junior level optics course at Georgia Tech. And the modern physics course is a sophomore level course that only assumes that the students have taken physics 1 and 2. And then it covers basically every field of physics. So it's a lot.
And it's like normal 3 credits.
Yes, exactly.
Is there a lab component? I guess there's no lab component. There's
no lab component at all to either of them. I mean, there are lab courses, of course, but I don't teach those and haven't. There's no, I don't know a good way to do that online. But the bottom line is you can download all of these lectures. And what I've done is I have the students watch them at their leisure, and then I use class time for discussion. But I literally tell the students, you don't have to be here. You don't have to come. If you don't have any questions, you're fine. And, the great thing is most questions that you get are clarification questions, but I've literally gone through 50 drafts of the script for each lecture. So there are very few issues that remain unclear after that many. I had a lot of time during the pandemic. So there are very few questions. A lot of the students have never shown up for class at all, but it's fine with me. They're doing very well. It's amazing.
That's the very British way of teaching, right? I mean, go to Oxford or Cambridge, no one comes to class.
Yeah. Don't get me going about that education model. But my goal is to teach the students better. And since I've taught these courses so many times, and I've spent so much time, I've really been obsessive about my lectures that when the pandemic happened, I realized I had time to narrate them all. And so I just said, I'm going to make them as professional as I possibly can, and then share them with the world. So no one else, my ultimate goal is to stop teachers and professors from having to prepare their lectures independently and redundantly around the world, which absorbs tens of billions of hours of human time every year and can be estimated to cost the world $1 trillion a year. And so I'd like to get some philanthropic organization to fund the creation of courses like I have done, which I did all by myself with a laptop and some, just some easy to get, not so expensive software, so that then people could play these lectures or let the students watch the lectures at their leisure like I did, and then use class time however you want. I'm using it to also get to know the students. It's really interesting to be on a first name basis with every student who shows up, and they're my friends now. So it's a really I want to change the world, and I thought if you're covering all of Africa here, that's I think Africa would be a great place to start the process. So and hopefully you'll all enjoy it and benefit.
Yeah, I think we can. We've actually so the African Light Source, we are trying to create basically a Pan-African synchrotron university, which is
excellent.
Be like a virtual university, but a lot of what we are trying to do depends on optics, right? Not only the beamline optics, but the laser matter interaction to create new methods.
Absolutely. Yeah. By the way, my actual field when I'm not doing this is ultra fast optics, and my contribution to ultrafast optics has been to figure out how to measure the pulses completely, both in time and space, with simple devices. So if you're ever interested in that, let me know.
Yes, I am, as a matter of fact. So one of the things that we gonna want to do, and we tried to do it this year, but we ran into problems, but do a tribute to Zwell.
Okay, great.
So I knew Zwell. He was always nice to me.
Excellent.
And then given this year's Nobel Prizes,
yeah,
it seemed to. So we've been working on a session on or whatever kind of tribute, whatever, on the basic theme is like from femto to atto. What do we learn with shorter pulses?
I just gave a talk on that, a public talk in Atlanta for the average person, and so I have a 1 hour talk. So if you guys have a slot open, hopefully at a more civilized time of the day for me.
Right. Well, you know, so I'm in the United States right now myself. So
okay.
I can yeah, this is hard duty.
Well,
normally, so when we have normal like colloquiums or whatever, we do monthly colloquia. They're at 1600 GMT plus 2, which is well, right now it's 9 o'clock. Because we Central Africa time does not do daylight savings time or anything like that.
I see. Okay.
So we could do that. I don't know if any of your work involve biophysics.
No, none of my work involves biophysics. Basically, what I do is I invent techniques to measure the pulses. It was an unsolved problem for decades because the assumption was that in order to measure an event in time, you needed a shorter one. And that's, of course, how Zwell did the great work that he did, understanding fast events in chemistry. But the question then actually arises, how do you measure the pulse? That's the shortest event you have, and maybe even the shortest event ever created. So that was a challenge that I took on and solved it in the 1990s. And the techniques that I've developed are still the gold standards in the field. And over the last decades, we extended them to pulses in time and space. So I actually have a recorded colloquium talk on that. And so it's very easy. Anytime you want me to give it, it's really easy. I just come
I haven't thought about that type of stuff. I went to University of Michigan as an undergraduate, and I knew her.
That was the nexus of ultrafast optics, but maybe it was before your time.
No, I remember when what's his face came to Michigan. I was
Gerard Monroe.
Yeah, I was there, and I knew Herb Winful fairly well.
Oh yeah, I know Herb. He's a good guy.
Yeah,
great.
I was an undergraduate when he came to Michigan.
Okay.
And Gerhard was, I remember when he came, and I remember when he left. I guess I was in graduate school someplace else when he left Michigan.
Okay.
But I do remember him being there.
Okay.
So now the the thing is, well, it was femtoseconds back in the day, right? And and Zwell once told me that, when he started this work, people told him that it would never work, that it would, and that he should try something else.
Oh yeah.
Now, what Zwell did is kind of passe, right? Because now.
Well, everything that was done, a couple of decades ago seems boring now, right?
Yeah, it seems boring now. So now we're giving Nobel Prizes for, 3 orders of magnitude faster, right?
Not a lot.
I often ask the question, like, well, I mean, how atto is chemistry? Like, how fast do you have to be, right?
Yeah, that's the thing. Attosecond. It's a little too fast for chemistry. I mean, not much happens if you just think about it. In 100 attoseconds, even an electron can't move very far.
Right.
So there's very little, I think, chemistry that is interesting on an attosecond time scale. Basically, the events that people are measuring with attosecond pulses are inner shell electrons moving. It's just such a short period of time that. I found myself saying, well, this is a really cool development, certainly deserving of the Nobel Prize, but we're probably not gonna learn a lot of stuff that we didn't already know. there's just not that much to study with them. So, but you never know. I mean, you never know. That's the nature of science, is the surprises.
Surprises. I knew a lot of Nobel laureates at Stanford.
Mm-hmm. Oh yeah.
Asheroff told me that his Nobel Prize was, I guess, luck favors the prepared mind, but if he would have never. And when I was at Michigan, this was a long time ago, Rudolf Mossbauer was at Michigan.
Wow. Okay.
Right. What a total nutcase he was. But people thought that he had broken the equipment, actually.
Oh no, really?
Yeah.
I have never met him.
Yeah, he was. Oof. I was like, so you are a Nobel laureate in physics, huh?
Well,
if
that's
you met him on the street, you think, who is this crazy dude?
Well, that's the thing about the Nobel Prize. They don't really care about your mental stability. All they care about is whether you made the discovery or not. It honors discovery. So a lot of people have done one thing and they get the Nobel Prize, and then they don't really do much else for the rest of their life. Then there are other people who win it for a lifetime of great work. So the Nobel Prize is, the average person doesn't realize how frivolous the Nobel Prize can be and how capricious the process awarding it can also be. But it's a prize. It's good. It glorifies science. And I think that's a good thing for humankind. So
okay. Fantastic. Well, we'll be in touch for sure.
Okay. Yeah. Thanks. Yeah. As I said, I was thinking of submitting a talk to this conference on my work in ultrafast optics because of the ultrafast light, of the light source that you're talking about. But I thought I can only get up in the middle of the night.
Right. Well, we'll come back to you on that. Maybe we'll do just one of our regular colloquia with you.
Oh, thank you. Yeah, I'd be happy to do it. Especially, as I said, I have a recorded 1-hour colloquium talk, which I can do via Zoom trivially. And that's on my website too. I have one of those other icons was called Research Talks and Short Courses. Right. And so, I have several narrated recorded talks that I used to give colloquia and keynote addresses during the pandemic. So those are easy for me to do. And so just anytime.
All right. We'll be in touch, and it'll be at a more civilized hour for you.
Yeah, thank you very much.
Okay, thank you.
All right, thank you.
Bye-bye.
Bye.
So Rosemary, if you can share your screen, you can start your talk. I think, well, let me check something. Where are we on time? So, Rosemary, you are here. It is 12 o'clock. I think Stephen is still not here. Rosemary, yes, if you could share your screen and start.
Yes. Please, I've shared it.
Yeah, I can see it.
Can you see it?
Yes.
Okay, thanks. Good afternoon, everyone. Please, I'm Rosemary Shen from the University of Education, Winnipeg, pursuing an MPhil in finance. And it's a study by Dr. Joseph Atufos and Dr. Amatu Yusuf and Rosemary Shen. And I'm presenting on their behalf. So the conference is on science and light, but we are on trading and economics and finance. So the paper is the terms of trade, institutional quality, and exchange rate volatility in West Africa. So we see that trading is the most commonest and the oldest form of international activity. And where countries export goods that they have in abundance and import the ones that are insufficient in their countries. And they trade using their currency, which makes the currency vulnerable to external shocks. Hence, institutions are needed so that they supervise and improve the predictability of the exchange rates. And there's an interconnection between exchange rate, trade, and institutional quality. So this study seems to find the link between these three variables. So we see that there are works on trade and institution, Dohan 2019, Ghani and Parasam 28, Gold and Rashid 2020 did a study on trade and institutions. Rajovic 2020 also examined the relationship between exchange rates and foreign trade in some selected European countries. Dodo also considered the role of institutions in assessing the effect of trade openness in Ghana. Ours is focused on bridging the empirical gap in West Africa. So we are motivated to. So our literature review, we see that there's merchandise theory where countries that are powerful seek to export more of the precious minerals such as gold, and in this case, crude oil. And the absolute trade theory propounded by Adam Smith suggests that countries should focus and export more of the goods that are in abundance and import the ones that they have disadvantage in. Likewise, the theory of comparative advantage. Again, North in 1993 suggested that institutions depend on external environment. Institutions, the external complementarities in the market affect an institution, and the new institutional theory bridge that gap in the old theory by saying that institutions should elaborate on rules and beliefs in their external environment. So others have done other theories, such as Dada 2020, found that there's a positive and negative exchange rate, found out that positive and negative exchange rate volatility negatively affected businesses in Africa. And that negative impact is greater than positive. Again, a study in Uganda by Truman Wine also said that there's a positive significant impact in the short run and a negative significant impact in the long run. Beidou and Japan also said that quality institutions have a positive impact on the financial sector. And due to the limited literature in Africa, West Africa precisely, our study is focused to clear some of these theories empirically. So this is a secondary data. This is an exploratory study that uses secondary data in assessing the exchange rate volatility on the terms of trade and institutional quality. We focused on the 15 West African countries, and the year was between 2000 and 2001. It's a panel data. Dependent variable is exchange rate return, while the independent variable is the financial development in terms of trade. And the financial development was picked from IMF database. It's an index. So we controlled using GDP per capita. And since West Africa is known for high debt, we controlled again for external debt and debt services. We have 6 individual indicators of institutional quality on the World Bank governance website. So we picked that one. Then we captured an index of the 6 variables. So we get a comprehensive research. And the data was chosen from World Bank, IMF, because they keep records and they are credible in their record keeping. So we use panel autoregressive distributed lag model, which is also known as the PARDL, because it will help us estimate the short and the long run parameters simultaneously. Again, with the Chromebook alpha reliability of 0.95, which is also the desirable outcome. We captured an index of the institutional quality. We use the PCA because it's been extensively used in other literatures. So this is the data and empirical analysis. And from this, we have the descriptive analysis of West Africa. So the observation for each was 305. Then from the descriptive, we find out that the mean for institutional quality index is the lowest with a negative 0.07, negative 0.007, whilst GDP had the highest mean with a 6.7059. We also find out that there's high external debts. There's high external debt mean. So you see that trade follows external debt closely, with external debt being 4.798. The terms of trade was 4.51, which was close. Also, the debt services, the term of trade and financial development was negatively skewed, while the others were positively skewed. Again, the ketosis value, we see that the debt services, external debt, inflation, and financial development also had a higher ketosis, which was more than 3, the value 3. We performed diagnostic tests on our results using cross-sectional dependency, the variance inflation factor, and we checked for probability and functional from using the Ramsey test, and they exceeded 5% to a significant level, which concludes that there was no problem of econometric estimation. Again, please can you see? Hello.
Go
Hello.
ahead. Yeah.
Yeah. Okay. So continuing, we find
It's
out
a little small, but I can see it.
Okay.
Is there a way to make this bigger? That's a little.
Is it okay?
It's a kind of a strange. That's a little helpful. Yeah. Okay.
Please, is it now okay?
Just keep going with your talk, and we'll figure it out.
Okay. So we find out that the correlation between the debt services and financial development was the least correlated, with the 0.072%, whilst the log of trade and institutional quality was the highest with the 46.4%. Again, since the debt services and external debt were highly correlated, which was normal of 0.963%. And we see also that the institutional quality indicators, that is the RQ, which is regulatory quality, CC, control of corruption, GE, government effectiveness, PS, political stability, RL, rule of law, VA, voice and accountability, were highly correlated amongst themselves. So this is the result of the cross-sectional dependency test. Then this is the stationary unit root test, which found all the variables to be integrated at first order, I1. So the variance inflation factor also suggests that there's no problem, since none of the mean for the VIF was more than 10%. Also, we see that from the Buchpagan test for heteroscedasticity, we see that there is no issue of heteroscedasticity, meaning they're all homoscedasticity, and the functional form was also good. This is the pictorial representation of the exchange rate and the individual variables.
Mm-hmm.
So this is the long run. Please, can you see? So this is the long run result of the term of trade on the term of trade institutional quality on exchange rate in ECOWAS, in the 15 countries in ECOWAS. So we generated 10 models. From model 1 to 6 is the individual indicators of institutional quality. Then 7, 8, 9, 10 was the index that we captured of the 6 variables. And we see that all the indicators of institutional quality had negative impact, significant impact on exchange rate, whilst regulatory quality was the only variable that had a positive, significant impact on it. Also, we see that when the index was introduced in the model 7, all the variables became significant except financial development. Again, in 8 and in 9, in model 9, we see that though the interaction of institutional quality and financial development itself was significant, the index of institutional quality was not significant. However, in model 9, both the interaction of trade on institutional quality and the index weren't significant, meaning the impact of institutional quality on trade doesn't have an impact on exchange rate volatility. And from the short run result, we see that only political stability had a significant negative impact, meaning that political stability is very significant and very responsive to exchange rate volatility. Also, we see that most of the variables weren't significant in the short run, meaning that in the short run, most of the variables had no impact on exchange rates. So these are the explanations. So I've said almost all. In effect, we say that the study fails to reject the null hypothesis that institutional quality had a negative impact on exchange rates in ECOWAS. Thus, institutional quality ensured stability as reported by North 1993, forcing 2016, and forcing ETEL 2020. These occurrences support institutional quality and the new classical institution theory. So in summary, we estimated the term of trade on exchange rate considering the impact that institutional quality had on these variables using an annual panel data from 2001 and 2021. These were chosen based on availability of data. The indicators of institutional quality, except regulatory quality, exerted significant negative impact on exchange rate, while the index, financial development, external debt, and debt services had mixed results. Most of the variables in the short run did not have any significant result on the exchange rate. GDP and term of trade were predominantly having a negative significant impact on exchange rate in the long run. So this study proves that external debt and debt services influences exchange rate volatility, because of the regimes, exchange rate regimes that we have, and because of the economic controls of the country. Hence, dynamic institutions in the exchange rates market is needed to produce counterproductive policies to ensure economic growth and stability. So this study proposes that West Africa should improve the quality of their domestic institutions in order to benefit from interventions and policies. Specifically, political stability and control of corruption needs a regional restructuring to ensure stability and discipline in the economic market. Thank you.
Thank you. This is a very interesting paper. There's one of the things I like to read from time to time is papers in econophysics.
Okay.
But also with respect to the African light source, this is sort of interesting because as we envision the facility, it would be sort of a multinationally owned. So you have multiple countries, multiple governments working together on a common goal, but you have widely different political economies. And so how do you fairly involve different countries that have completely different politics and sizes of economies?
Okay.
So that's an interesting question for us.
Yes.
Now, within ECOWAS, I mean, so which countries are the most stable and have the most stable monetary policy, since you're talking about exchange rates? And which ones are the ones where there are challenges in that regard?
Currently, we find out that the Anglophone countries are now quite unstable with a lot of coup d'etat. So most of their data were not available for the Francophone countries.
Right.
Because of the political instability that is quite becoming an issue now in the sub-region.
Right.
However, the non-Francophone countries seem to be stable for now.
Now, right, so the Francophone, Anglophone divide intrigues me.
Okay.
How do we bridge that divide? You know, I naively have said to people that I can't believe there's so much conflict in Western Africa over which European language people speak.
Yes.
And I guess it's more complicated than that, because it's not just the language.
Yes. You would see that the Francophone countries they all have a similar pattern, which seems to suggest that their colonial masters have kind of controlled them in a way. There are studies that seems to suggest that their former colonial masters seem to influence them in a way. So they have all the Francophone countries have a similar economic pattern which they follow. However, the non-Francophones, it's not the non-Francophones, because some of the countries weren't colonized by the English, so we say non-Francophones have different economic patterns.
Right. Now, in terms of their monetary policy, are there Francophone and Anglophone countries, do they peg their currencies to different ones? I mean, Now, I mean, it's
The
all the euro, right? But,
Franco,
do
the
Anglophone?
Francophones, yes, the Francophones peg their the Francophone is pegged against the French. Is West Africa West Africa CFA is pegged to the France, which is also pegged to the dollar in a way.
Mm-hmm.
But the non-Francophone, the word is non-Francophone, is pegged to the dollar.
Right.
Yes.
But Francophones, they peg to what?
They peg to the France Francophone, which is also pegged to the
euro, right?
Dollar. Yes.
Yeah. Yeah, that's problematic, probably.
Yes.
Well, it'll be interesting to how do we solve these problems, right? So corruption. I think corruption is probably not the gross problem that we think it is.
It is in West Africa. It is in Africa and West Africa, precise. It is.
Yeah, to me, it depends on what you call corrupt. But
okay.
I think one person's corruption is just another person's standard way of doing business.
Yes.
Well, thank you for your contribution. Is there a possible that you can send your slides for further analysis? I can do some further reading.
Yes, I sent it earlier.
Okay. All right. I will look it over, and I think I might have some further questions.
Okay. Okay. We'll be looking forward to you.
Okay. So I think that concludes this session. We start again in 1.5 hours.
Oh, I had a question.
Okay.
Oh, go ahead. I'm sorry.
This is Linda Trevino, Rick's wife.
Yes, go ahead.
He's gone to bed, but I just wanted to thank the host for being a fantastic host. And I just wanted to confirm, what is your name?
My name is Lawrence Norris.
Well, thank you, Lawrence Norris. You did a fantastic job with handling all the ups and downs of these timing zones. And I just wanted to express our gratitude for your fantastic hosting abilities. And have a good session.
Thank you. All right, we'll be in touch with Lee soon.
Oh, look forward to it, Lawrence. Thank you.
All right, thank you. Bye-bye.
Thank you. Bye.
Oh, Rick, we'll be in touch with Rick.
Oh, yeah, no worries. Yeah, and you have Rick's email. You have Rick's email, right, at Georgia Tech Physics.
I do.
Fantastic, Lawrence. Look forward to talking with you. Thank you.
Okay, bye.
Thank you.
Bye.
Bye.
Kathleen there, right? Kathleen, I'm really okay.
Hello?
Oh, okay. All right. I just want to confirm whether they are around or not. Well, the yeah. All right. Okay. Thank you for the
Philip was Prosper was supposed to chair this session. Is that right?
Yeah, I know it's not there. That's why I've not seen. That's why I have to be on board immediately. Yeah. All right.
I mean, I can do it.
We might need to start now, right?
So Emmanuel is here.
It's fine.
Karen Jacobs, I don't see.
Yeah, you are sharing for the end. So let's try to combine together.
And Gaston, I did see earlier.
All right.
Gaston
people already
was here.
Okay. 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 I think you can. I think you should stay at me.
Huh. What did I miss?
Okay, fine. Yeah. Okay, can we? It's left with a first name.
Kathleen is here.
Aaron. Jacob. Yeah, Jacob. Yeah, and yeah, I think it's fine. Bye. Okay. Okay. I think you can start now. It's already 1 o'clock now. Just try to once Prosper turn off, we will take over from where I stop. Yeah. Good evening, everyone. My name is Philip Olaji, my name, the conference chairperson, and welcome to today's session. And one thing I want us to pay in mind is if you try to be putting some content in the chat, because that will definitely help us to be able to for the presenter to look at the chart and to be able to answer us much better. But if you want to talk, we don't have a problem about that. So for the plenary talk today, this afternoon, it's going to be given by Dr. Kathleen Gorman, and the title of the talk is Proton X-ray Microcomputer Tomography on beamline BM18 and BM05 at the ESRS, and the current application in biomedicine, material science, and natural and cultural health. Over to you, Dr.
Thank you so much, Philippe. I'm just gonna, hi everybody. I'm just gonna share my screen. I hope everyone can see that. Can everyone see the opening slide? All right, so it looks like it's good. All right. Okay, so as I was nicely introduced, my name is Kathleen Dolman. I'm a postdoctoral researcher at the European Synchrotron and Radiation Facility in Grenoble, France. I work specifically on the two tomography, microcomputer tomography beamlines, BM18 and BM5. And today I'm going to present some very nice case studies we have from our team on the type of imaging, the types of results we've had in the fields of biomedicine, material sciences, and natural cultural heritage. So, okay, so many of you will understand this much better than I do as physicists, but essentially we use propagation phase contrast imaging on both these beamlines for tomography. And what this means is we have a partial coherent wavefront that interacts with the sample, and this creates interferences in the wavefront itself. And these phase fringes develop with a distance between the sample and detector, which the detector is able then to pick up. And we use different type of reconstructions, such as Pagan phase retrieval, to interpret these phase fringes and create final tomography data sets. So many might have seen this slide, but this is a nice example of difference between absorption contrast, which is essentially looking at the density differences within the sample itself. So this is of a amber fossil, and you can't really see anything just using absorption contrast imaging. But by just
Kathleen, your volume is tailing off. It's hard to hear you.
Oh, sorry. Okay, I will speak up. Okay, so this is using phase contrast. So we're able then to see quite clearly the insects inside the amber just by interpreting the phase fringes and reconstructing the phase fringes. So here is another nice example. So this is of a fossil dinosaur embryo, what we thought was a dinosaur embryo, but in the end turned out to be a reptile. And this is using the image created from using absorption. And then just by applying phase contrast, so increasing the propagation distance and retrieving the phase fringes, we were able to see quite clearly the different and quite numerous embryonic bones inside this little egg itself. So this is where I am at the moment. So I'm at the ESRF after its upgrade to the extremely brilliant source. And what this basically meant is there was a bump in the coherence and construction of new beamlines and refurbishment of existing beamlines. So for example, BM18, the beamline that I work on is a new beamline, and then BM5 had a very nice refurbishment during the upgrade. So these are the tomography beamlines that do some heritage. So there's ID16A and ID16B. This is a nanotomography beamline. And then there's BM18, which is a multi-resolution, high-energy beamline with a very large field of view for imaging larger samples. And then there's BM5, which is also multi-resolution, optimized for multi-resolution imaging. It has a medium energy range and a slightly smaller available isotropic voxel size for imaging. So let me just introduce BM5 briefly. So it has an energy range of between 35 and 130 keV on a filtered white beam setup. It has roughly available 6 meters for propagation phase contrast. The current tomograph installed can handle a sample size of up to 500 millimeters tall and 30 kgs in weight. And the available isotropic voxel sizes for imaging are between 0.35 and 25 microns. And there's a nice picture of Kuda scanning a very nice fossil on BM5 when he was a postdoc here at USRF. And then this is BM18. This is the new beamline. It's also optimized for propagation. Well, it was built with the idea of optimizing for propagation phase contrast imaging, and the idea for very rapid change in resolution. So we can do this type of hierarchical or multi-resolution setups for user and in-house experiments. It has a higher available energy range with up to 250 keV on a polychromatic beam. From source to the end of the experiment hatch, it is 220 meters long, with available distance between the sample and detector of 36 meters. Currently, it has exactly the same tomograph installed as on BM5, but in the future, once we finished installing it and commissioning it, it's currently being installed and commissioned as we're speaking. It'll be able to handle a sample of up to 2.5 meters tall and up to 300 kgs in weight. And this has quite dramatic implications for the different fields of research that are highlighted in my introduction. And the idea for this beamline is a high level of optimization so that we have efficient imaging of samples during an experiment. After the refurbishment, after the EBS upgrade, it has the smallest possible X-ray source of the EBS and the highest current level of coherence worldwide for high energy X-ray imaging. And the current resolution range available on BM18 is between 0.7 and 120 microns. So this is how we get that resolution range. This is our detector stage. I think it weighs 9 tons now. It moves on a marble floor, on air pads and wheels. And I think there are 9 detectors installed with different types of magnification, allowing for those different voxel sizes. And this is the camera that this new camera that was developed for a BM18 for this large field imaging. Beam size is up to 55 centimeters in width. So we want to image really large samples, so we need a really large detector with a larger available pixel size. This is the Iris 15. It's 5,000 by 3,000 pixels. Our previous detector was roughly 2,000 by 2,000 pixels. All right, so this is what we have. This is our current tomograph, rotation stage, and this is what we are installing and commissioning in a giant hole in the experiment hatch. And And what the idea is to be able to image a full human cadaver without having to partition the cadaver at all, to be able to image complete organic organ systems and a complete human system. And this also has implications for imaging larger industrial samples and also obviously for imaging larger cultural heritage samples. So this is sort of what it looks like at the moment. This is the large pit in the experiment hutch, and this is the Z-axis. The red is like the Z-axis pillars that are installed. This is not the most up-to-date photo. There's also the rotation stage that has been installed now. But this is to give you an idea of the size of the rotation stage. It's completely custom built for BM18. So what are we talking about when we are talking about multi-resolution imaging? The idea is to be able to get incrementally increasing levels of information or resolutions of information placed spatially within the larger context of a complete sample. So, for example, this is a jaw, a fossil jaw. I work on fossils. I'm a paleontologist, so this is I always try to use fossils whenever I can. So this is a complete fossil crocodile jaw, and I wanted to do some histology on it, and also to look at microwear on the surface of the teeth to learn more about its physiology. So I was able to completely image this large jaw, which was about 20 centimeters long, then completely image the teeth at 6 microns to get microwear and microsurface structures, and then to image at 0.7 microns a region within the tooth to get daily incremental lines. And this told me about how old this animal was, how it grew, etc., etc. Okay. Oops. Yeah, so this is a nice, so basically what's happening here is we wanted to show that we could rapidly change out between voxel sizes. So this was done last week, actually. So this is moving between 24 microns and 0.7 microns. And each resolution change took only 3 to 4 minutes with no need for refocus because we already optimized and set up, done a lot of commissioning on the detectors. So this is basically what is achievable within any given experiment. This is on a mammoth tooth. So we're able to zoom in and zoom out quite rapidly. Okay, so these are the current applications on BM18. Natural and cultural heritage, material sciences and industrial applications, geology and biomedical imaging. And I will give some nice examples from each one of these research areas. So first, I will do material sciences and industrial applications. This is the one that I know the least about, but okay, let's go. So this is a nice movie on airplane brackets that we scanned on BM18 from Fraunhofer. And what they wanted to look at was the porosity structures in the air bracket itself. And this has implications for its structural integrity. So it was scanned from 42 microns down to 0.6 microns, 0.65 microns. And what you can see is that the porosity, and as you increase in resolution to 2 microns, you're able to see the porosity structures, the surface structures of the porosity itself. It's quite rough. And then once you achieve the high sub-micron resolution, you're even able to see the orientation of the carbon fibers. And this is quite important for characterizing the material itself. And essentially the conclusion is would you really want to fly in a plane with a bracket that is as porous as this? So it has direct industrial applications after the study. All right, and here's another nice material sciences study. This is a watch that was scanned at a high energy laboratory by Fraunhofer and then scanned on BM18. What's interesting here is, so on the right is the slightly noisier one is the one scanned by Fraunhofer at the energy laboratory. And then on the left is the watch scanned at BM18. So the one that was scanned at the high energy lab was scanned over 24 hours. And the one on BM18 was scanned in 4 minutes. And from that, we're able to see quite clearly that there's an improvement in the signal to noise ratio. So here's a very beautiful rendering because that's the ultimate goal for tomography is make pretty images. And we're able to see each component quite clearly after imaging on BM18. So next application is in geology. So there's a current ERC grant happening between ID19 and BM18 to look at the origin of earthquakes, volcanoes, mechanisms of volcanoes, and how this affects climate change in the broader context. So this is volcanoes, which are currently quite, let me just go backwards, quite relevant globally, and particularly in Iceland at the moment. have quite broad implications, on not only just travel, but on development of geological systems, on climate. They're mass producers of CO2. So we want to understand how they are formed and also how we can prevent them, or at least not prevent them, but create awareness of when they're next going to happen, the type of implications they might have. So Benoit Cordnier is the one leading this ERC grant. And this is basically what he did was he created a volcano, a little volcano, but a volcano on BM18. So this is a nice in 4D, so scanning, I think, every 3 minutes. He did a scan to watch the generation or the change in the formation of the magmatic fluid as pressure was induced and heated. So he was looking at the bubbles, how the bubble structures were formed inside, and how this basically forced, and the intensity of the force of which it pushed the fluid out there. So yeah, we made a volcano. Okay, and then biomedical imaging. This is one of the largest applications currently on BM18. It's co-funded by UCL and the Chan Zuckerberg Initiative. And this is a huge team that's been looking at different aspects of investigating diseases. And they've come up with quite a revolutionary way of high resolution imaging complete organ systems. So where did it all start? It all started with COVID. So this was the initiation for the study and one of the primary funders for the construction of BM18. And this is the inside of the COVID lung. And what they wanted to do was look at the pulmonary vascular system to understand what COVID did and how it changed it. And basically what we're seeing here in yellow is once you are at an advanced stage in COVID, you hyperproduce vascularization, pulmonary vascularization to try to create different shunt systems within your lung, which don't work. But essentially you rapidly produce this intense level of additional vascularization. And this is where it all started. And the fact that they could see this in high resolution was proof of concept for propagation phase contrast and coherent imaging. So HIPCT, that's the team, is the idea of imaging a complete organ and then imaging different regions of interest at much higher resolutions. They want to be able to currently, which they already do, image intact organs. And then eventually, once we have protocols set up to image a complete organ systems, and then hopefully a complete cadaver. And the idea also is to, when you do these higher resolution areas, is to create registration very precisely. So, this is important for biomedical studies to know exactly where you are in the specimen and to register these higher resolutions areas within the precisely spatially in the context of the low resolution sample. And at the moment, they can reach a single cell resolution in intact human organs. So we'll see a little bit more of that. Okay, so this is how sort of the development of the protocol. So this is simple phase contrast. So this is when you do the reference or the flat field on the flat field of the beam. And you can see that there's not much you can see. You can barely see that there's an organ inside there. This is phase retrieval using attenuation protocol. So this is when you do the reference in the sample itself to try and remove as much background noise as you possibly can. And this is using dynamical optimization. Basically, you are sort of optimizing or trying to flatten the dynamic profile of the beam on the detector so that you are optimizing the contrast between the soft tissue and the reference itself, so the stuff that it's mounted in. And this, by creating this flat profile, you more evenly distribute your gray value ranges and be able to enhance the contrast. And then you get a very nice, beautiful soft tissue image. And then combine on top of that, you then do high resolution areas, and you can see some nice cells and vascular things and tissues happening in there. So this is a nice comparison. So this study this is of the brain, that was scanned at the same brain, was an MRI scan, scanned on BM5, and then scanned on BM18. The setup between BM5 and BM18 was basically the same, with the only difference of increased propagation distance. And you can see that increased resolution quite a lot in terms of what they could see of the tissues. I think they were even able to see some neural networks or some structure, but this essentially was a part of a clinical study where they wanted to be able to register the high resolution imaging that you see. This is a brain that was affected by Alzheimer's, I think. to resolve what you see in these high resolution areas directly against what you see in the MRI, so that you have clinical validation for the effects of Alzheimer's on the brain, and that has broad implications for researchers and practitioners, medical practitioners. So quite beautiful, lots of lovely pictures. And up to date, they've imaged up to 120 organs, including the brain, lungs, heart, appendix, liver, kidney, and the prostate. And each one of these are completely, well, not independent, but different, focusing on different disease areas and different types of diseases. And all this data is made online, freely available. The concept behind this project is for the benefit of researchers and medical practitioners to have access to this level of information to improve medical services. So here are some lovely renderings done by Siemens. They hired Siemens to do some images of the soft tissue organs. So obviously the biological information alone is quite significant. And they're able to render the tissues quite beautifully and get different layers of information. And this is all a part of the Human Organ Atlas program. As I said, it's a public database, image with HIP-CT. There's the link there, and you can download all the data and look at it and see what they've done. So finally, the remaining time, I will talk about some nice examples for natural and cultural heritage. So this is the area of the BM18 and BM5 that I work with the team. Me and Vincent Fernandez manage this. So I don't know if any of you have watched the Netflix or seen on Netflix. There's a recent documentary called Cave of Bones by Lee Berger, or involving Lee Berger. And this was scanning some hominidae fossils, which was scanned on BM18. And basically, this was supposed to be a burial site. And inside this burial site, there's preservation of a stone tool, which is rotating nicely bottom there. So originally it was scanned at because it's the largest sample we've scanned on BM18 so far, actually. It's like 50 centimeters high and 40 centimeters in diameter. It was really quite a challenge to image with the current setup. But we were able to do it with some complicated imaging techniques. There's us with the wooden chair. So this is a comparison between the medical CT, which was done in South Africa, and then with BM18 at 50 microns. Looking at, so what you're seeing mostly now is sediment, but you're starting to see grown bones of the feet come through. And they were able to basically superimpose the resolutions to increase the final resolutions of the final complete scan. And that's the comparison between what you get from medical CT and then from BM18. And here's a nice video that Paul made. This is the lab source, the medical CT scanner. And this is the stone tool that was placed inside this, that was preserved with the hominid fossils. And then this is in comparison with the BM18 scans of the stone tool, and what you can see on there, we were able to discern very microstructures, surface microstructures, which are important for understanding the use and the manufacturing and identification of the stone tool. So possibly how hominidae used the stone tool and how they made it. And even possibly how it was buried in the context next to these specimens. So these are like little scratch marks that were placed on they were chipped on the edge of the tool. Okay, so that brings on to the idea, a big component of imaging for natural and cultural heritage is non-destructive imaging. So the idea is we want to preserve these samples for future generations, and a lot of what we do is histology. So histology is essentially taking a cut through a fossil or a tissue to look at the micro-internal structures. Classical histology involves cutting the specimen and using polarized light to investigate it. We're able to reproduce that using X-ray imaging to create this virtual thin slice. So here's a nice comparison between polarized light, classical histology, and synchrotron histology. And we're able to see these incremental growth lines in this crop to be able to determine its age and how it grew. Also with that, you're able to do histology within the context of a larger specimen. So you don't have to subsection the specimen down at all. And so I wanted to take, and this will be the last thing that I talk about for the last 2 minutes, and then I'll let questions. But I had the idea of have this human atlas project. And I had the idea of what if you were to apply this whole system study, like you do with the human systems, to an entire paleo environment using multi-resolution imaging. Would you be able to image the smallest insects to the largest vertebrates? And would you be understand deeper context of the paleo environment, such as how they grew, how they lived? And the answer to that is essentially yes. I scanned over 204 samples of different types of things from a lagerstadt in South Africa, which is a site that produces intensively fossils. And these are some thin sections through the bones, and they were able to confirm that there were many different types of animals. They grew in many different types of ways, and how they developed were independent, and were able to increase our understanding of the diversity within this paleo environment. We studied coprolites, which is fossilized species, and these act as like deep time capsules because preserving microvertebrates and little insects 200 million years is quite difficult. And these act as preservational capsules, as well as they tell us about the deep time paleo ecosystems like food webs and so on. And this is with my PhD student, Shangale Montgomery. So we use multi-resolution imaging on many coprolites, and we find a diversity in the range of inclusions from this fossil lagerstadt. So we found microvertebrates such as fishes and everything like that, as well as the earliest preserved 3D insect, and this is from South Africa. So at this particular time period, this was the origin for all the major groups of insects we have around today. So this will be quite a nice result in understanding the early evolution of this quite diverse group. We found fish scales, insects, unknown inclusions, many different types of invertebrates, which we are still investigating. We were also able to study the disease present in this deep time period. So this was a fused vertebra and arthritic vertebra that was from an early relative of a dinosaur called the archosaur. It was scanned originally at Nexa, and we could see that the vertebrates were all fused together, but not able to discern much more clinical information than that. So I brought it to BM18 and I scanned it on BM18, and I was able to do virtual histology. And I was able to confirm against a bare vertebrate, which is the one at the top, and then the archosaur vertebrates at the bottom, that the internal structure of the bone is formed in the same way. So this will help us identify clinically what type of arthritis this was. I did histology on areas that don't have arthritis, so that might even give us an idea of age. So even within the context of this large, and this is from the same fossil lagerstadt, G-Fontaine. So we were able to discern diseases present within this community at the time. Another discovery was some of this fossil lag, this fossil lag deposit, which is like an accumulation, contained thousands and thousands and thousands of little jaws, which we attributed to Batoidia, which is the group that includes ray fins. And this is some of the earliest known deposits of ray fins, about 100 million years older than what we currently know. So this is quite nice for understanding early diversity of this group. And so to answer that question, yes, we can use multi-resolution imaging to even understand very large environmental settings, such as an ecosystem, using multi-resolution imaging, and be able to discern from parasitic level up to the largest vertebrate and how they grew and what they were doing, what diseases they had, and how they interacted with each other. So in conclusion, many broad and important impactful applications across a diversity of research fields, using different types of tomography at different types of sources. This is the team, and there are many of us. And yeah, with that, I would like to thank you for listening, and if you have any questions.
Right, thank you very much. I would like now the floor is off. Any questions you can ask, or we can drop it in the chat. Either way.
I just want to say it was always, for me, the most Damascus experience I've ever had of science was this particular subject. And I think it's absolutely amazing. It totally revolutionized several fields. So thank you so much for giving the talk, and I really enjoyed it. It's great to have it at our conference.
Thanks so much, Simon.
All right, is there any other questions? Yeah, I just want to ask if you are working on the geopolymer samples. What about the sizes? Do you talk about the sizes, or it's fine the way it is? Yeah.
The sizes that we're able to image of the samples themselves.
Yeah.
Okay, so at the moment, with the current tomograph stages that we have installed on both beamlines, the samples are up to 30 kgs in weight and about 20 centimeters in diameter and up to 500 millimeters in height. But once the large tomograph is finished being commissioned on BM18, depending on the density of the sample and a number of other perhaps factors that may affect the photon count, we should be able to handle samples up to 300 kgs and 2.5 meters in height and about 0.5 meter in diameter. So quite large.
All right, that's quite right. Then I think you should try to drop your email address on the chat, and at the same time, then I think I will contact you maybe via email to take it off from there concerning the geopolymer work that I'm currently working on.
Sure.
All right. So you want to say something, Lawrence? Because the next speaker. Okay. All right. And the next, thank you very much. Next speaker is a Professor Emmanuel Inji. We'll be talking the title of the significance of structural biology for Africa. Professor Emmanuel, the floor is yours now. Unmute yourself, please.
Oh yeah, sorry about that. Yeah, just for correction, Dr. Emmanuel, not professor. I want to thank the African Light Source Foundation and the African Physical Society for inviting me to present my research. The title of my talk is The Significance of Structural Biology for Africa.
Did we lose him? Uh-oh. Emmanuel, maybe you can turn your video off to preserve bandwidth. And share your screen again. And Emmanuel, you're muted.
Can you see my screen now?
Yes.
All right, sorry about that. So for the benefit of those who don't know me, I'm an African structural biologist. My research focuses on determining the structures and functions of drug targets. I'm also involved in capacity building for Africa-based researchers in structural biology. And I'm also involved in antibiotic resistant research to inform public health policy on antimicrobial resistance. So my talk is going to be divided into two parts. The first part, I'm going to highlight the significance of structural biology, how this has been used to contain some of the infectious diseases. So I'm going to focus on the African context. And in the second part of my presentation, I'm going to talk about BioStruct Africa, which is a not-for-profit organization focused on building structural biology capacity for Africa-based researchers. So what is structural biology? It's simply to take pictures of proteins and nucleic acid, and this is to see their molecular details and to understand how they perform their function. And this helps for us to understand disease states, and you can exploit that information for drug and vaccine discovery. So the usual scenario is to be able to explore a biological space where you identify a target gene of interest, you determine the structure, and then utilize the structure to explore a chemical space where you identify potentially a small molecule that can bind to the protein and disrupt the function, and this can be developed further potentially as a new drug. So structural biology can also help to reveal mechanistic insight. So this is an example of the mammalian fructose transporter. So by capturing the different states of the protein, how it moves substrate, fructose, from outside the membrane to inside the membrane, you can determine the structural transition that the protein undergo in a normal and a disease state. So the next example is sickle cell anemia. So on the upper part, this is the normal state where you have the hemoglobin, which is globular. So it's a tetramer. And in this state, the red blood cell is biconcave in shape, and this flows smoothly in the red blood cell, in the blood vessel. But in the sickle cell hemoglobin, a point mutation of the hemoglobin molecule causes it to oligomerizes, and this forms a clump in the red blood, and this makes the red blood cells sickle shape. And this forms a clot in the red blood cells, makes it not to flow smoothly. So you can see how structural biology has been helpful in this case to understand what's going on. The next example is malaria. So this is a project where I worked in my postdoctoral studies at Stockholm University. So it's a protein called the hexose transporter. It's from Plasmodium falciparum, the causative agent for malaria. So this protein is located on the surface of the parasite, which helps the parasite to capture sugar from the human cells. And this is important for the survival of the parasite. So there've been inhibitors for this protein, and most of the inhibitors, they had like moderate anti-malaria activity, but the lack of a crystal structure, has hindered the progress to develop these inhibitors further to target malaria. So our research determined the structure of this hexose transporter to 3.6 angstrom. As you can see, the sugar molecule is captured at the center of the protein, and we identify the key residues that are involved in the binding of the sugar and transport. So pay attention here that the resolution is 3.6, which is not good enough. So another group solved the structure to 2.6 angstrom, and they also determine the structure in complex with some inhibitors, which can be developed further as a potential treatment for malaria. So the next example that I'm going to explain for malaria is the Plasmodium falciparum chloroquine resistant transporter. So just to give you some context, so I was born in Cameroon, and when I was growing up, when we get sick of malaria, the usual treatment that our parents usually give us was chloroquine. But at some stage in my life, I realized that they no longer give us chloroquine anymore. And what's the reason for that? Because the parasite has developed resistance for chloroquine. And this is as a result of this chloroquine-resistant transporter. So it's also located on the surface of the parasite, which pumps out the chloroquine out of the parasite, which makes it difficult for therapeutic concentrations to be reached. So as you can see here, they've mapped out the different residues that are involved that have been mutated to cause the transporter to pump out chloroquine. And this information can be exploited in terms of optimizing the chloroquine molecule to be effective again. So the next example that I'm going to explain is COVID-19. So this is the timeline from 2019 when the first patient developed symptoms of Wuhan coronavirus. And in January 2020, the causative agent was identified as the novel coronavirus. So on February 2020, the first structure of this virus was determined and deposited in the protein data bank. And as you can see from, it's just 1 month period, the first structure was solved. And there are currently more than 1,000 structures of this from this virus deposited in the protein data bank, from the protease spike protein to the RNA-dependent RNA polymerase to the glucocorticoid receptor, which was solved in complex with dexamethasone. And this dexamethasone was the drug that was shown to offer some relief to critically ill COVID-19 patients. The next example is the case of influenza and HIV. So this is also one of the research I led at Stockholm University. So most viruses, such as influenza and HIV virus, before they could gain entry into the cell, they have to identify sialic acid on the surface of proteins before they can gain entry. So how is the sialic acid decorated on the surface of proteins was not known until 2019, where my research solved this mystery. So this is the CMP sialic acid molecule. It's being synthesized in the nucleus and it migrates to the cytosol. But glycosylation, where this sialic acid has to be decorated on the surface of proteins, takes place in the Golgi. As you can see here, there's a barrier, which means this CMP sialic acid has to cross this barrier into the Golgi. And how does it happen? It's as a result of this transmembrane protein called the CMP sialic acid transporter. So my research solved the structure of this protein using the lipidic cubic phase at 2.8 angstrom in the complex with the CMP substrate. You can see here at the corner of the molecule. So we've mapped out the different residues that are crucial for the binding and transport of the substrate. So using this information, we mutated these residues to see how they affect the transport of the protein. The transport of the protein, and as you can see, most of them diminish the transport of the protein if you mutate this to different residues. So most of them were mutated to alanine. So this diminish the transport of the protein, which is an indication of the of the residues that are important for the binding and to show that the substrate is in the right position. So the next example is the drug efflux protein. So these are proteins found on the membrane of bacteria. So what happens is if you take in antibiotics, these drug efflux proteins, they pump it out of the bacteria outer membrane or inner membrane, and this makes it difficult for therapeutic concentrations to be reached. So by blocking these proteins, you can restore the therapeutic effect of the antibiotics. So the next example is in the case of TB. So the original treatment was rifampin, as you can see here in red. This is the molecule that it targets in the bacteria, which is the RNA polymerase enzyme. So they've discovered a more effective antibiotic, which is called pseudouridomycin. And the reason is because the rifampin this is the active site. You can see this circle is the active site of the protein. So the rifampin binds somehow a little bit out of the active site, but the pseudouridomycin binds deep into the pocket. And this is now being used to treat drug-resistant TB. So the first part of my presentation, I have highlighted the importance of structural biology, especially in the African context, how it's been used to contain some of the diseases. The next part is to talk about BioStruct Africa. So in 2016, I attended the first Pan-African conference on crystallography. This was held at the University of Chang, Cameroon. So this is where I met my colleague, Dr. Daouda Traoré. So during this meeting, it was evident that the majority of the talks were not on structural biology. So it was evident that something has to be done. This was in 2016, and in 2017, when I was in Stockholm, together with my colleague Daouda and Dr. Mamandi, we established BioStruct Africa. And I'm the CEO and co-founder. Daouda is the co-founder as well as Mamandi. So the vision of BioStruct Africa simply is to train Africa-based scientists in the field of structural biology, to facilitate the relocation of Africans in the diaspora to establish themselves on the continent, and to actively promote the vision and roadmap towards building the first African light source. We want to form a consortium of Africa-based structural biologists working on prevalent diseases on the continent. We want to be a multidisciplinary organization with structural biology at its heart, and also to establish structural biology centers at African University. So what we want to see is to be able to actively conduct cutting-edge structural biology research at African University, to establish regional hubs for capacity building in structural biology through BioStruct Africa, and to offer structural biology services to African researchers through collaboration. So why structural biology in Africa? This is simply to support medicinal chemistry effort for the optimization and validation of drug leads, for drug discovery and vaccines, and also for new therapy, for new diagnostics. And above all, it's going to create jobs for Africans, and most importantly, the intellectual satisfaction of knowing how something works at the molecular level. The structural biology pipeline constitutes cloning expression of your gene of interest. You purify and do functional assays to be sure that the protein is functional. You can crystallize, or you do cryo-electron microscopy if the protein doesn't crystallize. In the case of crystallization, you do X-ray diffraction studies, process your data, refine, and do the model building. There are other methods of determining the structures, which I'm not going to go into. So basically in the cloning, you can use different hosts like E. coli, yeast, mammalian, and insect cell. So based on the origin of your protein, you can determine which host cell to use. For example, if you're expressing or producing a protein from humans, then you have to use a higher cell line, such as yeast, mammalian, and insect. But in the case of bacteria, you can just use E. coli. So once you've expressed your protein, you need to purify the protein to get a monodispersed sample. I'm not going to go into the details of the method. And after you've obtained a pure protein, you need to crystallize it. So you use different commercially available crystallization screens. And with the robot, you can set up plates and get your crystals. So basically, you have to expose your crystals to X-ray in order to collect a diffraction pattern. And this diffraction pattern you can use to build the electron density map, which you can use to build the protein model. So basically, it's just like going to the doctor and you expose your chest to X-ray to see the bones in your chest. So if your protein doesn't crystallize, you can do cryogenic electron microscopy, which I'm not going to go into details. So there are different synchrotron sources that can offer services for this, like diamond light source, which I'm currently working at the moment. There's ESRF, SLS, Max4, Soleil, etc. So what we've done is to structure the workshop into two parts. Firstly, the theoretical part, which we give them basic lectures on structural biology, protein purification, crystallization. And then the second part is the hands-on training, where we teach them how to crystallize protein. This was the first workshop we organized in Ghana. As you can see, we successfully crystallized lysozyme. As you can see, there is a happy face here bragging about the crystals. And the next step after you've obtained your crystals is to be able to collect X-ray diffraction. And this is where we really are lacking in Africa because we don't have a synchrotron. So what we're doing, we believe in BioStruct Africa that the poverty gap is a technology gap. So we're bridging this gap using the synchrotron remote access. So instead of flying to the UK for 800 pounds to collect data at Diamond Light Source, you can actually just ship your crystals to Diamond and then remotely control from wherever you are and collect your data and process and get your structure. So from the first workshop, we got really positive feedback and some suggestions and recommendations. So they wanted us to organize this workshop annually and also that we should increase the number of days for the workshop. So we responded and organized two workshops. One was supposed to be in the University of Rwanda, Kigali, and another was supposed to be at the Bingu International Conference Center in Malawi. But unfortunately, due to COVID-19, we were not able to organize these conferences. So we recently organized a workshop at the Malaria Research and Training Center in Bamako, Mali. So everything was the same, but this time we include some tutorials on cryo-electron microscopy. And also the feedback were very, very positive. So that brings me to the end of my presentation. I want to acknowledge the funders, Wellcome Trust, and also the Wenner-Gren Foundation, FORMAS, and Swedish Research Council, and lots of other participating funders. So that brings me to the end of my presentation. I'm happy to take some questions.
All right. Thank you very much, Dr. Emmanuel. A very good presentation, and which I believe going to help the continent as a whole. So yes, if there are any questions, for also ask. Okay, Trevor.
Hi, Emmanuel. That was an excellent and illuminating talk, and I was really intrigued about your workshops. I of course, knew about them. What I want to ask is, at how many sites in Africa has structural biology actually taken root? I would like to identify a partner institution in Africa that could that we could work with to expand more widely.
Yeah, thank you very much, Trevor, for that question. It's a very important question. So my understanding is that there are lots of groups in Africa. They're currently working on really important drug targets. Sometimes they purify the protein, characterize it, but then they lack that next step of determining the structure to get more structural information and also to exploit that for drug discovery. So there are lots of centers that I know, especially the Malaria Research Center in Bamako, Mali, in the University of Ghana. In Kenya, you have the Kemri Wellcome Trust that are doing some excellent research. But most of the time, they collaborate with groups in Europe for structural determination. So,
okay, let me rephrase the question quickly. If you were to put money in one group, which one would you select?
Well, I don't think it's
it's a hard question.
It's a hard question because I guess you just don't have to put money there, right? They have to demonstrate that they deserve the money, and it's likely going to be a competitive process. So whoever presents something that is reasonable, that worth funding, is going to be funded, right? But I know there are lots of excellent researchers in Africa doing this work, which I can say, yeah, the worth of being funded.
Okay. Thank you very much.
Yeah, so, Professor Kathy?
Yes. I have a question. First of all, thank you for that excellent presentation. So suppose a devastating pandemic hits 2 years from now, hits the world. That's sort of like the COVID-19. But at the same time, a devastating pandemic hits Africa and does not affect the global north. What would Africa do, given your understanding of infrastructures and people's talent? What would Africa do?
Well, I suppose this is the reason why we really taking the capacity building effort seriously, because we believe that, especially if you look at the case of COVID-19, within
I think we lost him. Okay, I retract my question. I will direct that in private to Simon.
Well, you know, that scenario has happened because there was Ebola breakouts while COVID was going on. Yeah. So,
but I'm talking about something worse than well, I don't want to say worse, but something that affects the whole continent at the same time, and it's not localized. Like COVID was not localized, you know, it was all over the world. So I'm talking about some virus that, for instance, some virus that likes dark skin, for instance, as an example, you know, in Africa. So, okay, anyway, I retract my question.
Well, probably just pray, you know, look for donor support. That's
but you're looking, but that I don't like. Okay.
Yeah, I think with Ebola in the past, and then in Africa, and there's one way or the other they managed to. I'm not a biological to be able to talk more about it, but it's a pity that Emmanuel will have the connection. But anyway, I think I would like to.
I think Trevor could comment because we have made vaccines in Africa.
Okay.
We have.
Okay.
And
during the COVID pandemic, the South Africans were quite effective in sequencing the new variants. And in fact, many of the variants were arising in South Africa, and they were rapidly sequenced, and the world was informed about the nature of the variants. So that was quite a good response. Our structural biology response, though, was pathetic. So we were completely incapable of doing structural biology in adequate time to do all the work that was necessary and the work that was done in the United States and China, in fact.
Mm-hmm. Okay. But that's the kind of question I think we need to put to the governmental officials, I think. What will we do?
All right.
Thank you.
I think we need to invite the next speaker, which is going to be Dr. Geron Jacob. He'll be talking about the African Bioimaging Consortium, strengthening the microscopic community on Africa. Over to you, Doctor.
Hi there, everyone. While I share my screen, can I just get a confirmation that someone can hear me?
Yes.
Perfect. Just looking for the right button. No, that's... Are you seeing my full presentation or my presenter mode?
we got the correct one.
The correct one. Okay, thank you. Hi, good afternoon, everyone. My name is Karen Jacobs. I am an imaging scientist at the University of Cape Town in the Institute of Infectious Disease and Molecular Medicine. As introduced, I'm going to be telling you about the African Bioimaging Consortium. I'm sorry I haven't been able to join in for most of this meeting, but I was able to log on at the tail end of what sounded like a very interesting conversation. So I think we all have shared interests in wanting to develop research capacity in Africa to support what is needed in Africa. And that was the root motivation behind the formation of the African Bioimaging Consortium. So to start off, a little bit different from, I gather what most has been discussed in this meeting, in that I'm an imaging scientist with reference to light microscopy, so photons more than X-rays and electrons. But the consortium is not exclusive to that. It's just an interest of a lot of the founding members. But the motivation behind why microscopy essentially was that more and more, especially with advanced modern light microscopy, it's being pitched as a fundamental and core research technology for the future. Whether you're looking at individual molecules and we're able to overcome the diffraction limit now with light microscopy, or looking at whole organisms or large volume and multidimensional screening of organs, organoids, small organisms, and even at an omics level, really modern microscopy has the ability to drive discovery and development all the way from single cell biology, understanding omics, histology, host patient interactions, drug screening, physiology, plant sciences, and soil sciences, for touching on food security. So really touching on almost all of all, I would argue, the research areas of interest that I think would be critical to research in Africa to address some of Africa's biggest challenges. But, and I'm sure this is not news to many of us, there are enormous barriers to accessing advanced technologies such as light microscopy, because it is a resource-intensive technology in the continent. And the obvious ones that we can all identify are sort of limited resources, and this means reduced or limited access to funding, which has knock-on effects in terms of access to equipment and to training and expertise. But Africa is an incredibly complex continent. It's not a monolith, and there are additional complexities that challenge access to advanced imaging technologies and to being able to really leverage these technologies as best possible by many of our researchers. Some of these are that due to cultural and complex historical reasons, a lot of research in Africa happens in silos. So even where researchers have access to this technology, they operate with very little support, very little sense of community, and that means no one knows what they're doing. And when they get stuck, there's no obvious avenue to getting support that really has relevance to their local setting. And this is linked to, so there's not really a large culture of informational sharing. There's language barriers across the continent. And to a large extent, we find when we chat to researchers that there's actually just not a lot of exposure as to what microscopy is there, what it can do, the potential that it has for research. And there's just the complete lack of awareness of what the power of microscopy for African research. So this is not to say that there is not research and good research being done in Africa. And I'm sure for this audience, I might not need to make this argument, but I've learned that I'll make it anyway. And that is, if you look at sort of some of these graphs, where the sort of showing the balance or the imbalance between the world population in Africa and the sort of shown in blue, and the red, the disease burden that Africa carries, and the green, much lower graphs, the research output. That the research output is there, it's just feeding primarily to the global north, as shown by these red lines in this chart here. Let me see if I can get a laser pointer. So this indicates, again, there is research being done. It's just not necessarily being done locally. And it means that there's a lot of handover of ownership of the research because it's dependent on collaborations with the global north. This is not inherently a bad thing, but the level at which this happens disproportionately to local research being done in a local context suggests that it is occurring from positions of imbalance of access and power. So all of that to sum up, to answer the question of why we want microscopy or really research capacity overall, because this doesn't happen in isolation on the continent, is because we want diversity in our research. We want equitable access to the technology, because we know that ownership of research is critically important, and that happens best when it can be driven where people are addressing the local needs in a manner that is seen to be most suitable locally. It also means that there's more opportunity for discovery. For those of us who have had access to this, we know the level of excitement and flexibility when you can walk down the corridor to go take a look at something with advanced technology versus having to plan a very expensive trip to an overseas collaborator with the one precious sample that you're allowed to ship. And as I mentioned, this is happening in parallel. So it's really this is a critical and important drive. And I think that's something that's sympathetic to this entire meeting, important drive to really advance research in Africa for Africa. As I've said, we're not starting from a point of nothing happening. And this was really driven home to us when we are here in Cape Town, just before the start of the COVID-19 pandemic in 2020, kind of as a trial run to see what was out there, ran a microscopy hands-on training workshop called Imaging Africa. And we wanted this to be fairly unique at the time, in that it was going to be was run exclusively for African students and researchers with some international faculty. And a key component of this was that with a large amount of external financial support, we could offer this to applicants at no cost. So cost of travel, accommodation, and all participation was covered for all selected participants. And we didn't really know what we were getting ourselves into, to be honest, because there was a great paper written by colleagues of mine with all the lessons learned from this, one of the key lessons learned is that there is an incredible demand for access and training in the continent. For a workshop of 24 positions, we received over 700 applications from across the continent. And where there are gaps with very few applications received, if you look at the language divisions across the continent, it suggests that primarily the shortcoming there was that we did not penetrate very well into some of the more Francophone and Lusophonic and Arabic-speaking regions of the continent. But nonetheless, we couldn't obviously support everyone, but we saw that there was incredible demand. One of the other take-home messages that we learned from this workshop in chatting with participants, both during and after the workshop, is that a lot of them, as I've mentioned before, work in isolation. There was some acknowledgement of challenges and disappointment that they were coming to Cape Town to learn about incredible high-dimensional advanced microscopy, with the awareness that they were going home to access to very little technology and very little ability to implement what they had learned. And this made us think a little bit differently about the capacity development that we were wanting to do. So in addition to our workshop, there are a number of other capacity development programs run throughout the continent, including locally. And some of those are as simple as open access core facilities, such as, given my local context, Cape Town, at University of Cape Town and University of Stellenbosch. A new initiative that I won't tell you about today, but also runs out of Cape Town, the African Microscopy Initiative, various societies and other programs looking to build capacity in Africa. And sort of, if we wanted to apply a critical lens, we could sort of divide these into two categories. One focusing on training, whether they're workshops or webinar series, is really focusing on a training of exposure to microscopy, and the others focusing on providing access to facilities, some of it cost supported, some of it not. And there was a very clear gap that we saw here in that, as hearing from people with the challenges they face, that they seem to be working in isolation. So we saw a need to build community around microscopy, and using that as a way to build community and supporting research in Africa as a whole. And from that came the Africa Bioimaging Consortium. So that's a long run-up to tell you about the consortium, which we launched first very informally and then more formally between March and May of 2021. And we were very fortunate that by January 2022, we had received funding for some of our activities from the Chan Zuckerberg Initiative. But we launched with the focus of being community-driven, wanting to empower the African bioimaging and microscopy community, and being open to everyone at all career stages, all levels of expertise, and including international partners, diaspora, and commercial partners, with the prerequisite that the focus is building African research capacity in Africa for Africa. And it's been very exciting because keeping our doors, so to speak, open, we've managed to build a community around ranging from people who are simply interested in microscopy and wanting to know how to gain access, to real experts wanting to build capacity in partnership with us, with an idea that as we connect people, we can build capacity, we can promote research, we can build dialogue and empower advocacy from an African community to policymakers, funders, institutions, and really enhance sustainability, because there's already so much out there. We're just wanting to enhance the sustainability and impact of those by connecting everyone as well. So definitely not with any interest in replacing or overcoming any of the existing programs, but really partnering and working out how we can do more better together. So as I said, since launching in 2021, we've grown quite rapidly. We now have engagement with over 262 researchers across 22 countries in Africa. And being completely open means that we have a large proportion of our community comprises of essentially early career researchers and postgraduate students, but also technical staff, core facility staff, commercial partners, lecturers. So it's really an exciting, diverse community covering all of the areas really of biological research of critical importance to the continent. And we've been able to map this community out at reasonable resolution due to one of the key activities that we set out to do right from the get-go, which was to literally build a map. And we've been a little bit cheeky that we've called this program the Microscopy in Africa Platform, which is abbreviated as MAP, with the intention of really increasing the visibility and accessibility of this community to each other, because very few of us have a significant or detectable online presence outside of programs like this, and then to make them more visible to the rest of the world as well. This is a way that researchers can find potential collaborators, potential students, access to equipment, and really in that helping to maximize existing resources on the continent while connecting them to the global, to the rest of the world. And this is done through a personalized Google map that it's interactive. So if one were to hover a cursor over, for example, that core facility icon, you would get the information about the equipment available there and whether or not it's available and who to contact. This is done through a Google form, essentially, with very simple information so that it doesn't take a lot of effort for people to complete, which has allowed us to get, as I say, a lot of information at fairly low resolution. I'll come back to this because we're wanting to increase the level of information we're recovering from the community. But to touch on some of our other key activities, we are, as I said, we're a community initiative. So our community is where everything happens. We have a number of online initiatives, mostly driven through working groups. At the moment, we have 3 active working groups focusing on training and education, where they've been working on building a targeted and tiered training curriculum for microscopy that can be taken on by interested researchers. They can learn how to teach it, and then they can teach microscopy in their local setting. Interestingly enough, even in this program, we've learned that there's a need from the already engaged community that more training is required before they can actually meaningfully contribute to this as they've started working on the higher tiers. So this is an opportunity for us to really reconsider how we are working with the community and what is needed. And that's something I'm going to come back to as well. And as mentioned, we've got this map that has fairly simple information that we now have a working group wanting to really flesh this out and is developing a survey to send out for a detailed landscaping exercise. So currently we're asking for information like, where are you? What institute are you at? Are there microscopes? What are they? And are they accessible? We're wanting to look at more detailed information, such as where were those microscopes sourced from in terms of funding, were they donated? What are the challenges around operating those microscopes? What sort of research is being used or carried out on those microscopes, to really understand what the situation and challenges are across the continent as much as possible. We're not expecting to get full coverage, although that would be nice, but as much as possible. And then to use that to advocate for what is needed in different settings. And then our last working group is a newer one that is focusing on how to create awareness around microscopy, as well as taking on some of the key communications activities of ABIC itself. To touch briefly, as the community is critical, we operate a lot online, which is something that we've all fell into very easily during COVID, but it's very important to be able to meet in person as well. So we started with our first in-person community meeting last year. And this year we were able to have our second one where we grew a lot. So we were able to maintain very interactive sessions. We had fantastic poster sessions showcasing of low cost and more accessible technology. And we even were able to get a little outside a little bit and see Stellenbosch where we were hosted. To go back to some of our online events, given that we're hearing from our community that they need more training themselves before they can in turn go out and support and increase sustainability themselves, we are looking at ways to provide soft skills and professional development. One of these is that we've already started is application writing workshops. The first series of these, we partnered with the Africa Microscopy Initiative, which hosts open calls for access to a large imaging center based here in Cape Town, and partnering with AMI, or the Africa Microscopy Initiative, as well as the HHMI and AIC based in the US, who runs a very similar program. We ran programs, a series of webinars and workshops for people interested in writing applications on what was expected and how to put together a stronger application than they would otherwise perhaps been able to do. This is the QR code that you see up there is one that is at this stage permanently open, that we're continually canvassing any participants for what else they want training on. And they've already given us ideas in terms of how to engage with policymakers, grant writing, putting together budgets for grant applications. So those are things that we're looking for partnerships with more experienced individuals and networks to be able to support our members with. Moving on very quickly, because I'm conscious of time. We always wanted our website to be a hub where researchers can find a lot of information. So through this hub, we list a number of opportunities and resources that are available to researchers in Africa, and this is continually updated. One of the ways that we do this is in partnering with Microscopy DB to provide a centralized list of upcoming funding calls, meetings, workshops, and making sure that they're really relevant to the research community that we're trying to support. And this is actually a very exciting partnership. This came out of, again, the COVID period, where a number of imaging communities around the world realized that we were all duplicating effort in trying to centralize and find information about workshops and calls and then put them out in newsletters. And we were all doing the same thing. So by creating a centralized database, or Microscopy DB, any initiatives that get added to the database get tagged with things like location, or if they're online or hybrid, if they're free, if there's a fee, what the topic is. And based on filters that are applied by each community themselves, these automatically get pushed to the interfaces on each of their websites to minimize hands-on time, but really make sure that information gets to where it needs to go. We also are building a portal of resources that in interacting with researchers, we're aware that should be easily accessible, but they're often just not aware of them. And based on feedback, we're actually building an annotation and ecosystem map for a lot of these, because even just having a portal like this for researchers completely new to the space, they're just not aware of how this all fits together. We partner with a lot of initiatives. For example, in this past year, we've had the exciting opportunity to partner with our French compatriots in France Bioimaging, and they've announced and fully funded themselves 2 calls for access to infrastructure in France, specifically for African researchers, with the idea that this will support research for Africa, but also strengthen bilateral relationships between the regions. And we're still waiting for funding, but through the Max Planck Bioimaging Network, they've been very interested in providing hands-on microscopy workshops specifically for African researchers that they will be able to run in Germany, and again, strengthen relationships and provide opportunities for researchers. We're interested in focusing on access and leveraging infrastructure that we do have in Africa as well. And with that, we, again, with generous support from Chan Zuckerberg Initiative, are able to offer mobility awards that encourage researchers to travel within Africa to different countries to access microscopy, either for pilot studies or on a collaborative basis. We have funding for 4 rounds of calls for this. We've had our first call, which was focused around pilot studies. We didn't have a great response to this, so we're working on improving that before we open up the next call later this month. But we did receive 12 applications with expected distribution of where researchers wanted to access technology. and we're excited to see what the next call brings. Coming to the end of everything that we do, hopefully in good time, just to acknowledge that everything that we do is dependent on incredible support and encouragement and partnership with a lot of other initiatives. And we've been very, very privileged, in addition to the Chan Zuckerberg funding that we received, to have strong partnerships with a number of entities, many of them, but not all of them, sort of displayed on the slide. And a lot of these have come out of researchers and networks around the world wanting to support and engage with what we're trying to do to build capacity in Africa and to increase that diversity and inclusion, which is very exciting. After this, I hope to be able to provide put a Light Source of Africa Foundation logo on the slide as well. So semi-last slide, just to indicate for anyone who would be interested in getting involved, that we do have some projects in development, one being some fora that researchers in our community have indicated they would like opportunities to engage in experts in some sort of fora or office hour setting around experimental design, designing systems, best practices for some of their research, and we're open to any support from the international community around that. We'll be launching, starting very soon next year, a mentorship program for many of our researchers, especially given that a lot of our researchers are early career researchers. And then ongoing, as I said, career development and training workshops that we're always open to support for with regards to that as well. So I will end with this slide with just an acknowledgement of all the people, and this is actually not a true slide because all the people putting effort into ABIC is the entire community, but we have a very engaged executive committee, which includes, has included 2 colleagues in Cairo and Senegal, as well as a colleague who splits time between Nigeria and the UK, working group coordinators who are incredibly passionate, and a very engaged scientific advisory board from around the world. And all of our details are listed here at the bottom of the slide. So for anyone who is interested in getting involved, please do reach out. And I'm going to end there. Thank you. I'm happy to take any questions if there is still time.
All right, thank you. A very great presentation and initiative, which I think is going to be a long way in improving our country. So colleagues, any questions? Cannot drop it in the chat box. You can try to ask or
Hi, I have one question. Thank you. That was a really nice talk. I wanted to obviously you're focused on microscopy, which is great, and obviously has very broad implications. But it is a nice sort of initial, like a network system, an informational system that you set up, and obviously you've got broader applications for bioimaging in general. Is it your intent, or do you think in the long run, perhaps the platform that you've initially set up for sort of light microscopy could be grown to include other types of facilities for bioimaging in a more general and in a larger context?
Yes, so that is something that we're looking at, and this is something that we get asked fairly often. Our initial focus has been light microscopy, partly due to the interest of the people who got involved in from the get-go, but also with the understanding that to a large extent it's a much more accessible form of technology to implement on the ground on a broad basis. Light microscopes are just a lot cheaper than electron microscopes and synchrotrons. But we do have significant and a growing number of community members interested in electron microscopy, interested in the implications of structural biology, and therefore to connect our researchers and to connect those opportunities and infrastructures in the community. There's definitely opportunities to include or at least formalize partnerships with various programs and initiatives around that. There is an existing African community network of a sort around biomedical imaging, specifically MRI. So we partner, and I acknowledge I don't think I had their logo on my last slide. They're called Camera, and I cannot quite recall what that stands for, but we do partner with them. And we're starting to engage more and more in the translational aspect of sort of biomedical to histopathology to advanced light microscopy space. But even as we say that, we're very aware that a large portion of our community kind of just is in need of a good wide field. So we're trying to meet a great spread of need as well as we can with the resources and manpower that we have.
I think Sekasi is asking.
Yes. Thank you for that excellent presentation. In the last talk, Professor Ng mentioned that if you have a protein that you cannot crystallize, then you can use cryo-EM. But I wanted to add that you also have X-FELs, X-ray free electron lasers. Could you say something about when you would choose one versus the other if you have a protein that you cannot crystallize?
I would be the first to say that I'm absolutely not the right person to answer that question, given that most of my approaches are around light microscopy applications in the UV vis range. My suggestion would be sort of single cell or single molecule high resolution microscopy, but that unless you're looking at sort of quaternary structure or complexes, is not going to give you the sort of structural information that if I understand correctly, you're asking about. But I'm happy for someone else to jump in and address this.
Yeah, maybe Professor Ng could say something if he's still online.
Yeah, I think it's for cryo-electron microscopy, you have the size problem. So you would ideally want to do cryo-EM if the size of the protein is decent enough to get the resolution that you need. So I think what we've done is to be able to increase the size of the protein. Sometimes we use fusion protein partners such as nanobodies or antibodies race against the protein. But if that size is not there, then I will go for the other option.
Okay, so you don't have you in the past, have you used X-FELs?
So I haven't really used X-FEL to say, but I've mostly worked on X-ray crystallography and cryo-EM. So like X-rays and cryo-EM, yeah.
Okay, so basically small proteins, X-FELs would be more appropriate if they're too small, and larger proteins, the cryo-EM. So they're complementary in that respect. Another question I have, and in fact, it was raised in Professor Ng's discussion that you can send samples remotely without traveling and have people there to take the data for you. In fact, that's one of the things that we do with the LAMP program. When we send people for training, the purpose is for them to go there, meet collaborators, because it's always good to have people on the ground, the staff beamline scientists. So when you send the samples, you're sending it to a close colleague as opposed to just in general. But my question has to do with samples that are very time sensitive. Have you, Karen, run into situations where you have a sample that has to be measured immediately? You don't have time to send them remotely?
Again, I can tell you about a opportunity that we do offer around light microscopy, but I'm not a cryo-EM person. But what we do have in Cape Town is an open access facility, as I mentioned, the Africa Microscopy Initiative. And what we actually have there is a visitors program and we've intentionally modeled it around providing support for researchers to come with their samples, and it needs to be that we have infrastructure to prepare samples on the ground from tissue culture and animal facilities, specifically to overcome some of these challenges that sometimes a box of FFPE tissue samples travels fairly well. A lot of other microscopy samples don't, so they need to be prepared on site. So we have visitors programs around that. I think I have heard about some of those as relates to CARIEM, but I will be happy for someone else to answer that.
I think I can chip in to add something to what she has said. So basically, for remote data collection, for X-ray crystallography, it's either you send your protein and then they crystallize it on the beamline, or you crystallize your protein and then you freeze it in liquid nitrogen and send to the beamline. For X-ray, for cryo-EM, you need to freeze your sample in a grid, yeah, and then you can ship that to the beamline for data collection. But in case where you have to send proteins, sometimes especially for membrane proteins, when you freeze them, they don't tend to behave well. They tend to aggregate. In that case, you need to send your samples fresh. And in that case, you really have to do things very fast because they are very, very prone to aggregation. So that's basically what I can add to that.
Okay, so for remote access, then you do have that situation where you have very time-sensitive samples that you may run into. So that's another reason for having a light source close by. Okay, thank you very much. Thank you.
Thank you, everyone. Thank you, the speakers and Dr. Carol. I mean, we really appreciate your talk, and I hope you drop your email in the chat box so that people can be able to. So for in case they have some questions or something across, they can be able to reach out to you. Okay, our next speaker is going to be Dr. Gaston Caballero. He'll be talking about new opportunities on the studies of matter at extreme conditions in the ESRF and the EBS.
Yes.
Over to you.
Hello, Chairman. Can you see my presentation?
Yes.
Okay, so first of all, I would like to thank you for the opportunity to present the results here, and also for inviting me and to try to transmit what we are doing today at ESRF. I will change a little bit the topic of the presentations. I will mostly dedicate to what we do on particular two diffraction beamlines. So let me just check. Okay, so this presentation will be, I will try to summarize a little bit what we are able to do nowadays in terms of extreme conditions at the SRF. And in particular, I will concentrate on two beamlines. Give me a second, I will use on two beamlines, ID15B and ID27, two beamlines dedicated to X-ray diffraction under extreme conditions. So first of all, why would we like to use extreme condition, and in particular, why we want to use pressure? Imagine that you are studying water. So if you look at the phase diagram of water at room pressure, what you see is that you have the liquid state and then one crystalline phases that happens when you cool down water below 0 degrees Celsius, in which you get one particular phase. But if you add if you add pressure, in that case, you can see here this new axis that appear on the bottom is in GPa, in millions of atmospheres. In 10,000 atmospheres. So if you add 2,500 atmosphere, you see that clearly the amount of crystallographic phases is huge. So it means that there is a very complex system and you can really explore the phase diagram. And for sure, you can really have access to very large region of your energy landscape in function of temperature and pressure. So that's why pressure and temperature together are very useful parameters in order to better understand your system. So in particular, where it is the high pressure and in particular extreme conditions are very multidisciplinary fields of research, high density physics, high pressure chemistry, air science, and then in the term of material science, and also we do some experiments on soft and biological matter under pressure. So in particular at the SRF, there are, let's say we can divide the activity in high pressure or in extreme conditions in two fields, one dedicated to static compression and the other to dynamic compression. I will mostly concentrate today on what is static compression, meaning using diamond anvil cells and large volume cells. And these activities are related and are extended in many beamlines, covering very large variety of techniques using X-rays, X-ray diffraction, absorption spectroscopy, inelastic scattering, nuclear resonance, and X-ray photocorrelation spectroscopy. So in particular, if we concentrate on, as I said, in diamond anvil cells, in which we have two opposed diamonds that will confine our sample here in this region, and we are able to reach pressures of more than 2 million atmosphere. We can couple this with high magnetic field, as you can see here, it takes a magnet, or we can cool it down to below helium liquefying temperature, or we can warm up either by resistive heating or by resistive heating, or with laser heating devices. So this allows us to cover very large phase diagram temperature pressure range, covering up to pressure of the order of 5,000 Kelvin and pressure of the order of 2 million atmosphere. So in order to give support to the users that come to ESRF to develop experiments, and in which in their own home facilities they don't have the possibility to prepare this type of samples and cells, we have the high pressure lab that is dedicated mostly for user support and to give access to the equipment needed for this type of experiments, and in which we can really cover, as I mentioned before, this temperature and pressure phase diagrams. So we give all the support needed in order to be able to achieve their experiments. So, and in particular, what we are able to do, or what we put a bigger effort, is on one side to the sample manipulation, meaning all the equipment that we need in terms of room, in order to premises, in order to be able to prepare your samples, to cut your samples and manipulate them, and also from the beamline point of view, all the setups needed in order to have the successful experiments during your beam time, and also the instrumental developments for the future experiment that nowadays we are not able to do. So now I would like to try to summarize what these two particular beamlines dedicated to X-ray diffraction, ID15B and ID27. These two beamlines are located in these two parts of the storage ring and correspond mostly to static compression, as I said, and there is a little bit of activity in dynamic compression using piezoelectric-driven diamond anvil cells. But most of the activity is on the diamond anvil cell in static conditions. So these two beamlines, in particular ID15B, is a beamline that is placed in a canted region in which two beamlines can work together. As you can see here, there are two tubes of X-rays going out. ID15B is located in this part and is a beamline that has a very high flux in terms of X-rays. We can focus down to 1 micron beam and also unfocused beam, so we can have a kind of continuous beam size ranging from 1 micron to 2 by 2 millimeters. We are working only at 30 kiloelectron volt. That is a good energy that we use for X-ray diffraction at extreme conditions. And finally, there are three types of technique that you can do, mostly X-ray diffraction in a nano and a micro beam with high resolution. We can also develop a high energy coherent X-ray diffraction imaging, and then some time-resolved X-ray radiography. At the same time, the other beamline that I mentioned before is ID27. That is a beamline that has been recently refurbished, and in which is a very long beamline. So the hatch is located at 110 meters respect to where the X-rays are generated. And again, here we can have a very variable focal spot size, ranging from 300 nanometers to something like 10 micron by 10 microns. And also we have the possibility to work in unfocused beam. Now the possibility in this beamline is we are able to change the energy from 15 kiloelectron volt up to 60, and we can couple X-ray diffraction with X-ray fluorescence, and again, high energy coherent X-ray diffraction and imaging, and time resolved X-ray radiography. So just to show you here, we have many setups, but the two more interesting one is the one on your left. As you can see here, is dedicated for low temperature studies on powder and single crystal. Here you can see the cryostat. On the back, you see the two-dimension X-ray detector, and the X-rays are coming from here, and then you collect and set at fixed temperature and pressure that we can change with the experiment your X-ray diffraction pattern. At the same time, you can also couple it with laser heating. Your sample is sitting here. You have two lasers coming from right and left, and then you are able to heat your sample and apply pressure simultaneously. That allows to cover you again the pressure temperature phase diagram as you can see here. So I would like to show you some examples on what we can obtain or what type of research, mostly dedicated to physics. What we are able to do is, for example, we can study glasses. As you can see here, this is silicon oxide glass that as soon as you apply pressure, you can see the modification on the structure of this glass. And the most difficult part is that in an amorphous system, the diamond anvil cell gives you a huge background that mask your signal, so it's quite hard to be able to obtain significant quantitative data in order to obtain the structure of your glass. So that's why we use this type of collimator that you can see here on your left, that allows you to really clean up and reduce the contribution of the inelastic scattering of your diamonds in order to have a very good data in order to be able to develop per distribution function studies. And this can be coupled not only with pressure, but also with temperature using either the low temperature setup or the high temperature laser heating setup, as I showed you before. So this is mostly dedicated on liquid and glasses, but most importantly, since the reconstruction of the machine and due to the availability of the new detector, we are able to really develop a single crystal X-ray diffraction. Here you can see, for example, the example of the structure of vanadinite. This is a particular mineral that in which we are able to really solve the structure of this material, and then we are also to develop in situ synthesis of new single crystals under high pressure and high temperature. And after this synthesis, we are able to really cover with these very small beams that we are available today to go and look on very inhomogeneous sample, one particular position of your sample, and then really do single crystal solution in this pressure and temperature condition. And this is one example of a recent user experiment, and you can see here a new barium nitride system. So following also the fact now the enormous win in photon flux and the new refurbished beamlines and the new detectors that are much more sensible, we are really able to go and look for very deep and very little details of the crystal structure, and in particular, for example, of this high TC superconductor, we are able to see here in this region of the reciprocal space this diffuse scattering associated with the charge density wave. These are a type of anomaly that appears in this part of the phase diagram, temperature doping phase diagram of this material, that can explain why we have this high TC, high superconductive temperature of this type of material. So this anomaly or this diffuse scattering, this signal is much weaker than the main Bragg peaks of your sample, and in order to have you an idea, these reflections are 6 to 7 order of magnitude weaker than the main structure. So nowadays we are really able to go to study this charge density wave reflection observed in this type of materials and follow it under the application of strain on this material. And as you can see, as you put a strain on this material, you see that this type of diffuse scattering that is very broad and large gets much well defined as soon as you apply a little bit of uniaxial strain, showing that you are really going to a 3-dimension characteristic of this charge density wave. And if you really want to push this type of experiments and we add high energy, meaning high resolution, and put energies on the X-rays up to 50 kiloelectron volt, we can observe that if we couple with very small X-ray beam, we are able to go to have access to the electronic density distribution and its evolution with pressure. And as you can see here, in the case of calcite, when you apply pressure, quite modest pressure between 1 and 1.5 GPa, we can really observe how the electronic cloud is modified. And in this orange region, these yellow regions, we see a diminution of the electron density that is along the oxygen-carbon bonding, and then an increase of the electron density along the unbonded regions. So we can really develop new type of experiments to really have access to the electronic density that up to date was not possible. And then also we can also profit again from this large dynamic range of the measurements, and we can perform diffuse scattering at high pressure, as you can see here in this particular compound, in which we can really solve and see how the the diffuse scattering gives you information about the elastic constant and how the structure is affected by temperature and by pressure. And you can really obtain information about, for example, in this particular case, how the antiferromagnetism appears close to the quantum critical point. Other point that is really now a new type of experiment that we were not able to do before is exploit the coherence of the beam at 30 kilo electron volt. We have 2 order of magnitude more flux than what we had before, and this allows us to really push now and develop X-ray imaging exploiting the coherence of the beam. So for this, we can develop imaging, and in particular, the example that I would like to show you is this example of high pressure Bragg coherent X-ray fraction imaging, in which by scanning the one X-ray Bragg peak, we can really reconstruct the shape of a nanoparticle. So this is a particle of the order of less than 500 nanometers, in which we were able to, through the reconstruction of these Bragg spots, we were able to reconstruct the shape of the particle and, more importantly, the strain inside the particle. So with these examples, I would like to thank you for your attention, and I would like to share with you all the people that collaborate in the preparation of the construction and the construction, and the commissioning of these beamlines, from the beamline and also from all the groups that are able to put this project together and to the good end. And also with this, I would like to thank you for your attention.
Thank you very much. Great presentation. Now the floor is yours. Any questions, please? Any questions, if you ask or drop in the chat.
Yes.
Okay, there's no question. I just want to ask something. What is the energy level? Because I don't know, maybe I didn't listen, of the equipment, as well as the temperature ranges.
Sorry, again, which is that?
The energy value of the equipment as well as the temperature ranges, because I'm trying to look at materials with of a high atomic energy. So what is the energy value for the
energy
system?
Yeah, so the energy we are working at is mostly 33 kilo electron volt, 33 kilo electron volt, but we can go to higher energy to like 60 is the maximum we are able to achieve in this type of experiments.
Oh, okay. Wow, that's cool then. We can need to come to the SRF and see most of this unit in a while.
Yep.
All right. So, I think thank you very much.
Can I quickly ask?
Oh, okay. Yeah.
Yes. I cannot hear you very well. Sorry. Cutting.
Okay, Simon.
Just hold on.
Yeah, no, it's okay.
That now? I know like a holy grail of this kind of measurement has been metallic hydrogen.
Yes.
You know, I was just wondering if you can say anything about that or closer to that.
So yeah, the difficulty of hydrogen, it is very light element, and again, as I for the case of the glasses, to be able to get the crystal structure, let's say we concentrating mostly on crystallography. We did some experiments. We managed to get close to the metal, the insulated to metal transition. We didn't manage to solve the structure at this really high pressure, but it's getting more and more possible. But the real, yeah.
Do you think it will be achieved with a diamond anvil cell?
Yeah. So let's say there is an experiment made on at Soleil, in which they measured infrared spectroscopy, where we really show that there is a closing of the gap and the sample is getting metallic. So this was published, I think, 1-2 years ago, in which it was really shown from absorption that from infrared absorption that the sample get metallic, and so from let's say we are in phase 2. The only question that remains to be solved is which is the structure, the crystal structure of this system, but this is still a little bit hard for us. Let's say now the equipment is able to reach the development of the diamond anvil cell allow us to reach these pressures to achieve this half a terapascal, let's say. But now the difficulty is to be able to obtain X-ray diffraction out of it. This is a
That's
challenge.
amazing.
Yep.
Oh, thank you.
Okay. Okay. There's a question in the chat for you. There's a question there. That's you might need to see. Okay. The person was like, do you find some examples of industrial material research at extreme condition beamline?
No, let's say there is a little bit of research under extreme conditions for application, but the main activity, I would say, close to 99%, let's say, full of activity at the moment is academic research, fundamental research. There is a little bit of material research in terms of synthesis of new material, of new materials, but the industrial activity is not mainly on at extreme conditions. There is quite a lot of activity on characterization of already synthesized materials, but not to push on the synthesis itself of new materials. This is still a new field to exploit and to go for it.
All right. Okay. Thank you very much. I think before we call it a day, I would think Simon will help us. I want people to just open there so that we have some pictures before we end this session. I don't know whether it's okay like that.
Yeah.
Can just, so Simon, you will help us, or Lawrence help us to take the pictures. Everybody should try to put on their camera on so that at least you can have always need to look at the picture.
I think we all put on our cameras and all look straight at the camera. Hold your smile for some seconds. Please hold your smile. And I'm seeing if I can get one. Yes, we fit everyone on. I'm going to take a screenshot. So counting down, 3. Oh, one moment. 3, 2, 1, 0. There we go. That was everyone. Thank you, folks. You looked very beautiful.
Thank you.
So, Catherine, how many minutes you want to give us for the next session? Because you'll be sharing it.
Okay, so the next session would have started at 4 South African time. So let's meet back in 10 minutes at 4:05 to do the next 10 minutes. 10 minutes tea break.
Okay. So
okay.
Let's start with the all right. Cheers.
Okay.
Yeah.
Hello.
Yeah, everyone's at tea for another 3 minutes.
Okay. Tea for another 3 minutes. They're out for tea for another 3 minutes. চারটের সময় হবে এখন এটা সাউথ আফ্রিকার টাইম এক্ষুনি এটা বন্ধ করে বাই চান্স কোনো অবস্থা বন্ধ করেন না হ্যাঁ এটা বন্ধ করেন অফ করো ঠিক আছে ভালো Hello.
Hi, Tapas. Your chair is Kathleen.
Hi. So
She's there, yeah.
nice to meet you.
Yeah, I'm Tapas Ganguly. Hello.
Okay, so all right, so this is the next invited speaker for this afternoon's talk, Dr. Tapas Ganguly, and he is going to be talking to us about the status and capabilities of the Indus 2 at the Raja Ramana Center for Advanced Technology. If you'd like to share your screen and go ahead and present your talk. Thank you.
Yeah, I'll share my screen. Hello, is my screen visible?
Yes, thank you.
So good afternoon, everybody. And I'd like to start by thanking the organizers for giving this opportunity to me to present on behalf of our facility, Indus 2. And I'll give you a update of the kind of work that we are doing specifically towards the research in material sciences. And before, of course, that, I'll give you a brief review of the facilities that we have. So the plan of the presentation is as follows. I start with introduction to Indus synchrotrons. I give a brief details about the beamlines at Indus facilities, some examples of interesting research work, and there's two examples specifically on the research work that myself and my colleagues are involved in related to intermetallic alloys and large bandgap oxides. Before I go about the presentation, I would like to use this opportunity to express my sincere thanks to all the people who are responsible for all the data that I'm showing here, the users who have been using the beamlines, and the beamline scientists who have been, worked a lot to make this facility available to all the users. So this presentation is on behalf of all of them, and a thanks to this whole team. Okay, so we start here with a brief view of the Indus synchrotron facility, or the Indus facility as such. We have a microtron, which is the source of the electrons, is a 20 MeV microtron, which feeds electrons to a booster synchrotron, which increases the energy to about 450 MeV and injects the electrons into the Indus 1 storage ring. This is a very small storage ring, a 450 MeV storage ring. And in the case of filling for Indus 2, the booster jacks up the energy of the electron beams to 550 MeV, and then it is injected to Indus 2, which is a 2.5 GeV machine. So the electron is accelerated, electron beam is accelerated 2.5 GeV and is available for the users at Indus 2. So the Indus 2 has 18 operational beamlines currently, 16 of them available to users, and 2 of them are supposed to be designated for machine diagnostics. Indus 1 has 7 operational beamlines. Indus 2 is a double band achromat lattice with a periodicity of 8. It has provisions for 5 insertion devices, out of which 3 of the insertion devices are operational. This facility is available round the clock since February 2010. Of course, Indus 1 is a pretty old machine, which was initially commissioned in 1999, and Indus 2 was formally commissioned in 2005. And from 2010, it has been available as on the round the clock mode for users from all over the country, and in fact, from many other places around the world. So I briefly talk to you about the various some images that show you the different facilities. This is the Indus 1 storage ring here. This is the section of the Indus 2 storage ring. These are the insertion devices here, which are there in Indus 2. This is the front ends of Indus 2, and this is the view of the experimental hall in Indus 2. So if you look at briefly what are the facilities available on Indus 2 for users, this is the list of all the beamlines. So we have various applications which are possible through these various beamlines at Indus, which includes absorption measurements, engineering applications, essentially an X-ray diffraction-based beamline to handle engineering components. We have a reflectivity beamline for the soft X-ray. We have an imaging beamline for various kinds of medical engineering applications. We have lithography. We have EXAFS beamlines. We have a beamline for extreme conditions, X-ray diffraction, where we do high pressure and high temperature measurements. We have a general purpose X-ray diffraction beamline, a grazing incidence X-ray scattering beamline, primarily meant for thin films, photoelectrons per hard X-ray, photoelectron spectroscopy, X-ray fluorescence microprobe, small and large wide angle X-ray scattering beamline, protein crystallography, and the 2 diagnostic beamlines. In addition to that, we have those ones in blue, which are on insertion devices, more recently commissioned, which are the angle resolved photoelectron spectroscopy and X-ray magnetic circular dichroism beamlines. Some of them are under development and at various stages of development, which includes the atomic, molecular, and optical sciences beamline, which should be available very soon to the users. The extreme conditions XRD beamline with a superconducting wavelength shifter. We have a project of development of a superconducting wavelength shifter, which will enhance the available energy of the photons up to 90 keV. And we also have a plan for a protein crystallography beamline on a Wiggler, superconducting Wiggler, and some other beamlines which are in the planning and initial stages of design and development include the spectroscopy for scattering in the intermediate X-ray energy range, which is typically from 2 keV onwards to about 9 keV, and radiation safety studies beamline and photoemission electron microscopy beamlines. So if you look at the typical user data here, besides this COVID years of 2020 and 2021, when the number of user experiments were really very small, we could not have people physically coming to the Indus beamlines for their experiments. We are typically close to around 1,000 user experiments annually. In fact, this data is for last year, 991. This year, we are surely to cross 1,000 user experiments. And if you look at publications, we are typically around 175 publications annually. This could be going to around 2,200 this year. So we have research scientists and researchers from all over India coming and doing experiments, and from more than 150 different institutes regularly come to these beamlines. It is important to note that the Indian industries are also regularly using our facilities, especially the pharmaceutical industry in India, which is quite a developed industry, has been very interested in using our facilities and regularly are kind of using it, and this usage is continuously increasing. And we have also used our facilities for several projects of national importance for our country, which includes the projects from the Indian Space Research Organization, ISRO, for the lunar missions, which we call as Chandrayaan-1, Chandrayaan-2, and more recently Chandrayaan-3 also. You may have heard about these missions in some time in the past. And regarding the protein crystallography activities, which is one of the premier activities in the biological application sector, we have more than 160 plus structures which are deposited in the International Protein Bank, which have been solved using the data collected at Indus beamlines. So here I will give you a brief idea about the various facilities. So we have the angle, I mentioned about the beamline. So we have the angle dispersive X-ray diffraction beamline, which works in the 4 to 25 keV energy range. And it has got both a goniometer and image plate, and some of the details are shown here. All these details are also available on our website. So I'll just very briefly go through them. This is just to give you a sense of the feeling as to what are the kind of facilities we have and which is available for users on a routine basis. So we have also got I mentioned about the extreme conditions X-ray diffraction beamline, which is primarily meant for high pressure measurements and high temperature measurements. We have engineering application beamlines, which is primarily meant for engineering components with a specially designed experimental station that can handle up to 15 kg samples. So typical industrial components can be directly measured and can be directly analyzed. And we have also a small and wide angle X-ray scattering beamline, which I just mentioned, which is available for structural analysis at the mesoscopic length scales. In the absorption domain, we have a soft X-ray absorption beamline. So we have a hard X-ray absorption AfPS beamline, which is one of the most, I should say, beamlines on demand today. And we have a lot of facilities to perform in situ and in operando studies. I'll give you some examples of this also as we go ahead. We have a beamline for soft X-ray absorption measurements in the energy range of 100 to 1200 EV. And here also we have a lot of demand, especially those who are working in chemistry and chemistry and different chemistry related problems. They find it extremely useful. And more recently we have set up a magnetic dichroism, magnetic circular dichroism beamline, and very few experiments have actually been performed by users in the last 1 or 2 months of its regular operation with users, but more and more interest is being shown by several users, and we expect this to be one of the very attractive facilities for studies of magnetic systems in the near future. Besides that, we have an angle resolved photoelectron spectroscopy beamline, which in fact, I have been extensively involved in its development, design, and final implementation. Personally, I have been involved in this beamline also. And here we are in a position to go to a resolution of 20 milli-electron volts at 30 eV, 30 electron volts of photon energy. This is designed on an undulator, and this has been extensively used by the condensed matter physics community in the country in the recent past. We have a for X-ray fluorescence microprobe beamline, where we are in a position to focus the X-ray beam down to 4.5 into 7 micron size and do an elemental scanning and mapping of sample surfaces. And in general, of course, we can do lots of measurements on X-ray fluorescence, direct X-ray fluorescence, not the microscopy one, but just X-ray fluorescence measurements can also be done, and are done routinely by mainly biologists and chemists and other people. And we have also a facility for total reflection XRF, where we can go down to sensitivities of parts per billion also, which we have demonstrated in several samples for several users. The imaging beamline has facilities for absorption contrast, phase absorption imaging, phase contrast imaging, tomography, and laminography, and has, again, considering the energy range of 8 to 35 keV, this beamline is absolutely, in great demand by our medical community, which finds, and people who are working on low atomic number materials, and they find it extremely useful. And we have a soft X-ray reflectivity beamline, which is mainly meant for thin films, analysis of thin films, multi-layers interfaces, and buried layers. And the wavelengths of operation are typically in the soft X-ray part from 100 eV to 1200 eV. Now I'll give you some examples of interesting research work carried out by users at Indus Beamlines. This work which I'm talking about is actually, it also gives you a fair idea about the kind of cutting-edge research going on in several universities and institutes in the country, in India, and who have been using Indus facilities. So I'll just, on their behalf, just mention these results and some basic experimental facilities that have enabled these research to be accomplished. So this is a work done by an institute called the Indian Institute of Technology in Bombay. You may have heard about this institute, which is a famous premier engineering institute, as well as an institute for various kinds of materials research and basic research. And there's a very strong group that works on lithium-ion batteries in this institute. And our main aim was to study the in operando studies of lithium-ion batteries. That is, you actually subject the battery to some potential. You either use it, you are basically operating the battery, either charging it or discharging it. And simultaneously, you're trying to see what is the change in the chemical state, what is the change in the coordination number, what is the change in the chemical compositions, etc., while this process is going on. So this is one of a very important study to essentially improve the characteristics of the battery, which obviously need to be used for very long periods of time, it needs to be sustained for very long periods of time and long numbers of charging and discharging cycles. So we have a complete facility to do these in situ measurements, and as you can see that we have the X-ray source on this side. They actually goes through the sample, and on the other end you have the various diffraction techniques for making the measurements. For example, you can do Zane's measurements, X-ray absorption, near-Earth spectroscopy. You could also do diffraction measurements, and so on and so forth. So some of the interesting papers are related to studies of the moly ditelluride anodes and of different types of different phases of molybdenum ditelluride. And you can see in the last few years, there have been some very high impact factor publications from this beamline on these, on this particular work of lithium-ion batteries. This is a work on in situ study of X-ray spectroscopy of cobalt catalysts. Again, the catch here is the ability of our facility to be used for studying a reaction while it is in progress. So it's an in situ study. In this particular case, a Fischer-Tropsch reaction, which is basically for generation of methane from carbon dioxide and hydrogen, has been studied, and various forms of the catalysts have been characterized using the processes, using this cell that you can see here, the cell specifically developed where the reaction is going on and the X-rays are coming in and they're going out, and you're measuring the X-ray absorption spectra through the systems developed. In addition, you also got a facility of gas chromatograph, online gas chromatography measurements, which help you to analyze both the gas species as well as the X-ray absorption spectra simultaneously when the process of catalytic reactions are in progress. And essentially, the deactivation of the catalyst is the main point of concern here, which has been studied. And in 2019, we had a very paper in Journal of Synchrotron Radiation from this work. The material science community, as it happens in most synchrotrons, has been very active, and they have been using our diffraction beamlines extensively for phase analysis. As you know, that although the diffraction as a technique can be carried out extensively on a lab source, but with the synchrotron and its high intensity, we are in a position to find out very small minor compositions, minor phases, or very weak peaks, which help in determining the crystal structure in a more accurate way. So in this particular work, which is done from a team from IIT Kharagpur, which is another premier institute in the country today, you can see that the gadolinium chromium oxide, which is prepared by solid state synthesis, is paramagnetic at room temperature, and two different techniques of growth of gadolinium chromium oxide was studied, and their crystal structures were compared. So it is previously known that low temperature phase of orthorhombic PN2A1 structure was stabilized at room temperature by spark plasma synthesis method, and the high resolution low noise XRD data helped in resolving the fine differences in the XRD pattern of these two phases, that is the GCO and the spark plasma synthesized GCO. GCO is gadolinium chromium oxide. So very minor differences in the X-ray diffraction pattern, as you can see here, and in the zoom to blown up in the blown up data here, explain the ability to detect very minor differences in structure, composition, and in the phase of materials through these peak profiles. And very minor, small, very low intense peaks could be very easily discernible from the X-ray diffraction data that we can collect at the beamlines here. Here are two examples of, again, quite varying ranges of interest. This is a work where some hazardous red mud, which is a industrial waste coming out from these metallurgical processing industries, are studied, are analyzed for their content, metallic content, and then converted into diagnostic X-ray shielding tiles through a ceramic route. What is important here is to analyze multiple phases, not one, but multiple phases, so at the same time through the diffraction data. So it is very important to have extremely good quality diffraction data with a very low noise and a very strong data as a very high signal to noise ratio of the data. And that is again achieved very routinely for at these X-ray diffraction beamlines at Indus 2. And I show you this example to highlight the ability to resolve multiple phases in a mixed system. And this is a work where the thin films of titanium nitride, aluminum scandium nitride superlattices were analyzed, and the interface properties were actually looked into through the process of reflectivity, soft X-ray reflectivity. I mentioned about soft X-ray reflectivity as one of the major techniques in one of the beamlines. So this is where these kind of superlattices have been used, and these superlattices are extremely important and are a very interesting material for research in the for thermoelectric applications. So here again, we show you the ability to resolve very fine differences at the interfaces of different materials. And basically what we are trying to do is with the reflectivity data, we are trying to model it and trying to see which model is closer to the closest to the reality. And this of course helps eventually in optimizing the properties and the thermoelectric characteristics of these multilayers. Yeah. So here I show you data of X-ray reflectivity of a boron carbide chromium mirror, which is studied at elevated temperatures. So boron carbide is a very standard material which is used for X-ray reflective coatings on mirrors, and will be furthermore useful in materials in systems where the heat load is very high, for example, the next generation synchrotron radiation sources. And it is very important for one to understand how the structure of the material changes as a function of temperature, because the temperatures could go very high in the X-ray mirrors when they are exposed to very brilliant or very bright sources of bright X-ray sources. So the carry-home message in this experiment was the ability to do reflectivity measurements at high temperatures, which is what we can do very easily in the X-ray reflectivity beamline, soft X-ray reflectivity beamline in the Indus 1 facility, and very soon we'll have it in Indus 2 also. So this is what we have. I want to just mention here that the changes in the reflectivity profiles, as you can see here, as a function of temperature has been clearly recorded, and they have been modeled to understand how the interfaces between, let us say, the boron carbide and the underlying chromium, or the boron carbide and the underlying and the above surface layer, and similarly between the chromium and the but I mean, obviously present silicon dioxide on the silicon substrate, how these interfaces are changing as a function of the temperature at which the layers are kept for during the measurements. So this is essentially telling us the thermal stability of these systems. This is an example where we have used the lithography beamline to make a corrective X-ray optics, elements, X-ray optical elements. As you know that there's been an increasing demand and increasing desire to reduce the spot sizes of X-ray beams which are being used. So in this work, this work has been done in collaboration with the Diamond Light Source UK, where our role had been to fabricate these structures, which are some materials which are transparent to X-rays, but with different thicknesses, thereby creating a different phase shift as the X-ray beam passes through. This phase shift, which is introduced in this part of the, which is shown here, essentially corrects for the errors in the successive optics to get a sharper focal spot as compared to a case where this is removed and only the mirrors are used to focus. Or if I put it another way, there are errors on the mirror surface which increase the spot size of the X-ray focal spot. Using these correctors, one is in a position to get much smaller focal spot sizes. These were fabricated using X-ray lithography at the BL7 Indus 2 beamline and used at the Diamond Light Source UK, and the other two more recent publications coming out from this work. So the last two slides I have are related to a brief review of the materials research, which is typically carried out at our division. Of course, our division has several materials research activities. I will touch on two of them, which have been of interest to me in person. The first one is a study of a large bandgap semiconductor, an oxide large bandgap semiconductor, which is P-type. As you know that P-type large bandgap semiconductors are a more difficult set of materials to make, primarily from the basic physics that the valence band is composed of holes which have very high effective masses, thereby making the P-type conductivity quite difficult. Chromium oxide is, although a well-known P-type conductor, but it's got a poor conductivity for the very reason I just now mentioned. The whole effective masses are quite large. So our approach has been to substitute gallium with which has unfilled P levels, thereby that increases the oxygen 2P and the chromium 3D level hybridization, thereby increasing the conductivity effectively by reducing the effective masses. And we have successfully grown this gallium chromium oxide thin films on sapphire substrates, and their effect with nickel substitution has been studied. Nickel increases the p-type conductivity significantly, as you can see here in this curve. So what we try to understand in this work is, first, to see how the photoelectron spectrum changes when we are talking about a pure chromium oxide and when we are talking about a gallium chromium oxide. How the oxygen peak, you can see that in the gallium chromium oxide, the oxygen 2p part of the spectrum shifts actually closer to the valence band, thereby increasing the hybridization of the oxygen 2p and the chromium 3d levels, thereby increasing the conductivity also. In contrast, if you take chromium oxide, the oxygen 2p peak here is shifted about an EV or more away from what it is in the case of gallium chromium oxide. So this difference, or this change in the valence band spectra, is directly responsible for the increased p-type conductivity in gallium chromium oxide. And with nickel substitution, which is a 2+ ion substituting a 3+ gallium site, it improves the whole concentration, thereby increasing the net conductivity significantly. So these experiments of photoelectron spectroscopy were carried out at Indus 1. And more recently, we've also worked out the band alignment from photoelectron spectroscopy. We've tried to understand what are the ionization energy and what are the work function of the system by carrying out the measurements of the band structure at close to the valence band data close to the valence band, by excitations close to the valence band by a few 30 or 40 eV kind of excitations. And so this is a work which is continuing, and we've got some decent publications in the recent past. So this is a more recent paper where we showed the role of nickel substituted gallium chromium oxide. And in an earlier work, which is a little bit old, we had clearly shown the physical reason behind the increased p-type conductivity in gallium chromium oxide as compared to gallium oxide. Okay, this is the last slide I have. And this slide gives you data related to a half-Oyster alloy, COMnSb, copper, manganese, antimony. And what we have tried to understand here is how the structure of the system evolves as a function of X in CO1 plus X MnSb, and how the magnetic properties of the system changes. Are there any phase segregations and things of that sort? It is very important to note here that COMnSb is a half-Oyster alloy, which is supposed to be in what is called a C1b structure. However, by very careful analysis of which is shown here, the C1b structure is shown on the top here. Right. However, a very careful analysis of the X-ray diffraction data shows that actually the structure is not so simple, but it forms a superstructure, which is shown below, where the cobalt atoms, which are sitting at the center of these Mn and Sb cubes, are not arranged in the form shown here, but they actually form some arrangement which is shown below. This arrangement increases the magnetic moment, although the total mass or total formula unit is identical, is the same, which is itself a very interesting fact. And when we increase the cobalt concentration, we find that the maximum amount of cobalt that can be accommodated in the structure is only 0.45, only up to 0.45, beyond 1. So this is COMnSb, and when we start putting extra cobalt, where do they sit? So that has been analyzed. And the superstructure I just now mentioned is responsible for the increase in the magnetic moment from 3 μb to 4 μb per formula unit, which is a decent amount, which is 45, which is a 25% or 30% increase. And the key to understanding this property was a very detailed and a very involved X-ray diffraction data analysis and ritual refinement, which was possible because of the high quality of the diffraction data. This was a part of the PhD thesis of my student, which the paper got published last year in 2022. So essentially, in this work, besides doing these measurements with X-ray diffraction and trying to understand the structure, the magnetic moment was also measured and was compared with theoretical calculations, first principles calculations, and were found to be very, very good agreement. So this was one of the points which I wanted to bring out, where the strength of our diffraction data analysis and the capability to get very high quality diffraction data is the key to this research problem. So I would like to conclude with these slides and once again thank the organizers for this opportunity to me, and a big thanks on behalf of our center for having been given this opportunity at this very prestigious African Light Source Conference platform. So thank you very much.
Thank you very much for your very interesting talk, Dr. Ganguly. There isn't time for questions, but I invite you to put your email in the meeting chat for anyone who might want to send you an email to ask you more specific questions. So we'll move on to our next invited speaker, Prosper Ngomgonziza, who will be talking to us about angle-resolved photoemission spectroscopy at synchrotron light source. Prosper, are you here? If you are.
I'm here. Do you hear me?
Yes, I see you. Thank you. Nice to see you.
Okay, good. Nice to see you. Good. So I'm going now to share my slide. Let me share my slide.
Thank you.
So do you see my slides now?
Yes, it just needs to be put, yeah, exactly like that. Perfect. Thank you.
So let me put this one. Okay, good. So can I start?
Yes, please go ahead. Thank you so much.
Okay, yeah, thank you very much for opportunity to speak within this exciting conference about the African light source, and also as a part of one who is in the African light source. Also, I say thank you to all the organizers, also all the who are giving all the nice presentations. So for this presentation, I will try to highlight one of the experiments I do with my collaborators, where we use light sources, and the specific technique we use at light sources is the angle-resolved photoemission spectroscopy that I will be abbreviating by AfPS. And some of the experiments we do at the light source, and also some of the experiments we do in-house also, where I'm located at Louisiana State University. So as we may all know, this is a layout of the general light source, and we know from such a layout of a light source, we have different beam lines. And for me, I will be focusing in one of those type of beam lines where we use it mostly for soft X-rays for angle-resolved photoemission spectroscopy. And basically, the technique we use start from what we call photoelectric effect. And by photoelectric effect, we have actually, we eliminate our sample with lights. So with lights, and when we eliminate our sample with lights, so when the photons come to the sample, they kick out electrons. And these electrons that are kicked out, then they are collected into a certain specialized equipment that we call electroenergy analyzer. Then from that electroenergy analyzer, we can now map out what we see in the band structure of the sample. Basically, in a simple words, the main idea is photo in, electro out. And those electro outs, they are the one we analyze. Also, maybe you may also be aware that Einstein, of course, he is very well known for his theory of relativity, special theory of relativity, and the general relativity. But you know probably that actually the Nobel Prize he got was not in the relativity, but it was on the explanation of the photoelectric effect, which also highlight how important is this technique. And also later, almost 60 years later, also Kai also got actually also a Nobel Prize in 1981 about the tool photoemission as an analytical tool for development of the photoemission as an analytical tool for sample surface characterization. So this is to highlight how actually this technique is useful, and also it is addressing problem or in physics or other type of sciences, the problem which are very important. So, but on the one hand, of course, in the previous slide, I showed that we do the preliminary thing is to do photoemission spectroscopy, where you have the electron, the photon in, then electrons are kicked out, and you measure those electrons. But one also can do much more specialized, which is now the angle resolved photoemission spectroscopy, where we don't not only take a single electron, but also we measure electrons taken at different angles. Then we can map out the for example, things like the film surface of the sample, and also different features in the band structure of the sample. So now for this case, for example, we have the photons coming in, and then for these photons that these electrons that are coming out, we can know the takeoff angle. Then from the takeoff angle, we can also map out in the energy analyzer. When we are collecting the energy analyzer, we can then end up having the binding energy as a function of the momentum. Then you can have a complete picture of the band structure of a specific material that we are investigating. Yeah, so the key thing with the photoemission, the angles of photoemission spectroscopy, as I was indicating, is that we can have both can actually from the kinetic energy, which is measured of a certain material, we can analyze the data, and those data we are analyzing actually they give us actual information about what is happening inside our sample. So we can get actually the band structure of the material we are measuring. Then we can have a ability to understand what is the electronic structure, and also try to see or at the film level actually what is the physics which is happening at the film level of these systems that we are investigating. Yeah, so then also one thing we need to take into consideration is as a simple kind of brief theory behind it, is that in a vacuum we have the kinetic energy of the electrons, but in the solid we can now using these conservation laws we can actually have from the what you have in the kinetic electron in the vacuum, we can actually map out the binding energy and the momentum of the electrons that you have actually collected from the sample, which as I indicated gives the band structure of our material. And from this this layout of how the measurements look like, we can from these equations actually get the expression of the energy, the binding energy as a function of the momentum. In the principle, we measure the angle, but the angle can be converted into the momentum using these expressions. Yeah, so of course there is always different options of doing this angles of photoemission spectroscopy. One can, for example, do using a lab source-based experiments where you have, for example, helium lamp that you are shining on your sample, but that will be at a specific photo energy. These days also people can also do laser AfPS. But on the other hand, one can also do actually synchrotron-based AfPS, which gives much more advantage in the context that you can, for example, cover a wide spectral range. And when you are covering a wide spectral range, this gives much more advantage because you are now able to, for example, do the so-called matrix element effects due to the different photon energy you are using, and also you can change different polarization of the photons of the incoming beam of light, which can give you the ability to probe different features that you could have in your sample. And also the intensity is also highly polarized in a continuous spectrum, which are, for example, two of the advantage. Of course, there are other many two of the advantage one gets when you are using AfPS at the sequence light sources. So what I will do in the remaining few minutes, what I will try to do is now to focus on some of the specific examples that we studied, and of course there are many materials that we studied. I will only focus on one system, and on that one system try to demonstrate actually how we have been using AfPS to study that system, and the project has been evolving and new learning much more physics in that system. So now I will start with the project where we wanted to understand the band structure of a material called the strontium movement in the stoichiometry of 4310. And the first data that I will show are the one that has been presented in this recent paper 2020. And the good thing also is you can see it is a collaboration which brings together researchers from Africa and also researchers from outside Africa, which also I think is the key point for the African net. Also what we are trying to do, to see that we are not only hopeful in the future, we're not always the suitcase scientist who goes to the light source, but also we can have a light source in Africa and do this type of experiments on our continent. So the system that we were investigating, the experiments were done at the Soleil in France. So on the left side, I show the picture of the outside picture of the Soleil light source, and we use the beamline called the Cassiope at the Soleil, and the photon energy we're using at Cassiope, they have the photon energy from 8 to 1500 EV, and also for our measurements, we could measure at very low temperature down to 5 Kelvin in ultra high vacuum conditions. So on my right hand side, I show, for example, how the AfPS setup at Cassiope looks like. So you have the beam, the incoming beam, then also we have now our analyzer, and from there, once the electrons are kicked out from the sample, we can at some point get in the energy analyzer, they get now correct the band structure of our samples. So this system that we investigated, and also are still investigated, is interesting in the context that is in the system called the strontium movement systems, and these layered systems, they are interesting in the context that when you see, for example, is you change the number of this octahedra from the single from the n equal to 1 to n equal to the double layer to 3 layers and all the way to infinite layer, the physics change. For example, in the single layer, you have, for example, it is a superconductor, which is still a debate to whether it is an accommodation superconductor or it is a standard superconductor. Then once you shift from single layer to double layer, now you lose superconductivity, but you get interesting a system which is close to being ferromagnetism, and also this interesting metamagnetism in the system kick in, but you lose superconductivity on one hand. Then when you shift again to add one extra layer in the 3 layers, now you have now very clear ferromagnetism, and also the metamagnetism also persists in the system, and then you can continue all the way to infinite layer. You still have ferromagnetism and the other itinerant ferromagnetism in the system. The key message here is the system is interesting in the context that there is a lot of physics that can be investigated by changing the number of the fermion oxygen octahedra in the system. So what we have been trying to contribute more also in these systems is in the past, the band structure of these systems, either in the single layer the double layer have been, even to the infinity layer, they have been investigated very well, and also both on the band structure calculation point of view and the AfPS experiment point of view. But there have been, so before we contribute into this project, there have been no contribution regarding the AfPS, so experiments on the how does actually the band, the film surface of this system looks like for the three-layered system, and also the film surface of the three-layered system from the band structure calculation point of view. So what we did then in the paper I showed earlier was actually to do where they did the investigation using AfPS of the band structure of the system. Then you can get the film surface maps. You can map the film, get this film surface where we can, for example, have different film surface sheets which contributed to different type of electronic behavior in the system all the way to the film level. Of course, when we did this AfPS experiments at the Soleil, as I indicated, of course, there was still an open question, actually, how does it compare to theoretical predictions? Because if you have this AfPS map, there are also some fine features which is not easy to understand only based on the AfPS. So theory would be very interesting to understand what the fine feature. For example, if you go in the double layer system, this is what the AfPS experiment showed, but when you go in the theory, so you can actually have these also fine film surface sheets, which also can be much more explanatory when you compare with the AfPS experiments. So after we analyzed this AfPS data, so we then the project actually became much more interesting in the context also that I think Richard Martin also indicated it yesterday, that we wanted to have a much more thorough understanding of the system. Then I was in touch with Richard Martin, and in the context of assessment also, I think Richard Martin introduced assessment yesterday, which is the African School on Electronic Structure, Method and the Application. And then we started a collaboration. We often call it a three-continent collaboration on a three-layer RoofNet. That time I was still in German, so we can see people from the USA, Africa, and me who was located in German, doing a collaboration also with core international collaboration that involves now scientists from all these continents. So then Garu did a lot of work in doing band structure calculation, and then also from there we could also report our data in this paper we reported last year. And as I indicated, you can see we have a contribution in which it is a contribution you have authors coming from different continents, but doing science for the benefits of also doing this nice collaboration, which keeps is also still going on. So from there, then we could, in general, also get an overview of how actually the band structure, the theory can predict how the band structure could look like of this system, which I think now I would say now we can have a kind of a complete picture on the band structure calculation point of view and AfPS point of view of all of these three systems now, which can be compared in order to understand the physics in the system. One thing also I'd like to highlight is this system that we call the 4310 systems. One of the key physics that it has, which is interesting, is the so-called metamagnetism. And the prediction was actually this metamagnetism is due to the fine feature, which are very close to the Fermi level, which can be due to when one switch on the magnetic field, they can be the origin of the metamagnetism in that in this system. So actually, also when we finished to do this theory calculation, it also raised much more questions that we could do. We needed to understand, and then what we did also was actually to extend this collaboration and do more synchronous-based AfPS experiments. And one of the things we want to do is actually doing spin resolved AfPS, because for the previous AfPS experiments I showed, it was only angle resolved, so we didn't know about the spin orientation of the electrons were were measuring. So now we also had Jonathan, who is at the ALS, who also is a beam scientist there, who did a lot of contribution now to do the measurements on the same sample, but now with the focus more on the spin aspect of the samples we're measuring. And the good thing, we start to do these measurements during the Corona time. And during the Corona time, one of the good thing is we can do remote experiments. For example, here I was with Jonathan, but this time I was sitting in my room at home, and Jonathan was at the beamline. And we could do experiment and they run all of the experiments together, and they try to control the things. And sitting at home also, I could be able to control all the things that one can control remotely in the software, for example, for different type of the measurements. So which is also one good thing I think is good for this type of collaborations. When there is possibility to do online experiments, that's something I think gives much more also freedom when the time doesn't allow for traveling. So the work also we did for this spin resolve the AfPS for studying the band sort of the system. So we reported it also in this recent paper that we uploaded on the archive. So which is under review. And the key message here for this recent paper is the fact that we can now also get through this now where we can not only do angle resolve, but also spin resolve the measurements. We can get actually better understanding of the film surface maps that we are measuring. And when we do actual comparison with theory, we can now get a deep understanding where we have the spin majority side, which film surface map actually from this film surface map. So this side, for example, we have much more the spin majority, and down here we have the spin minority. So which is, I think, also another big contribution in understanding better the physics which is happening in this system that I'm not going in detail to explain for now in view of time. So lastly, what I would indicate is that in my research also, what we are doing at the LSU, one of the things also which is ongoing is to try to do actually AfPS, but on thin films, not on single crystals. Because for the other these samples, the previous samples I was showing for 4310, they were single crystals. Now we want to move to using actually thin films, then do photoemission spectroscopy at the light source. And the good thing also is at LSU we have a 1.3 G electrovolt a sync control. It's not a fancy one, but one can do already some preliminary measurements. Then for good samples, also go to much more advanced light source. So in my lab, what we do basically, we used past the laser deposition to make the thin films. Then from those thin films we can characterize in situ using, for example, X-ray photoemission spectroscopy. Of course, when we are growing samples, we can also use reflection, high energy diffraction to actually monitor the surface quality of those thin films, and also this also gives the flexibility to control the film thickness. And the dream is actually to interface a vacuum suitcase to this system. So in which now, because the goal is, if you want to use thin films, you need to make sure your surface doesn't get contaminated or because it is exposed to ambient condition. So how we do it, one, put a vacuum suitcase on the system, so you can transfer samples from in vacuum to a vacuum suitcase, which is like this suitcase. Then you can transport your samples to a light source. Then to a light source, one can now connect to a photoemission setup and do all the necessary experiments without exposing sample to ambient conditions, which I think is something cool and interesting, which also protected the samples. Then you see what I call the novel physics, and see the novel physics without expose the sample to ambient conditions. So with this, I think the time is running out. I would lastly indicate that we need a light source, an African light source, because there are many reasons. I think men have been elaborated on this. There are a lot of science we can do when we have a light source in Africa. And for me, my case, I was trying to elaborate is the case of material science, where we can use science, for example, a light source, for example, for mineral characterization and so on. And hopefully in the near future, we can have a light source in Africa which can contribute in all aspects of scientific discoveries and industrial innovation, having socioeconomic impacts, capacity building, for example, training of PhD students and so on and so on. So I think and I hope in the near future we can have a light source in Africa and address or have a science in all these fields being done on our continent. So with this, I will finish here, and with this summary of my presentation, then I will welcome your questions or input, and thank you very much.
Thank you, Prosper, for that really good talk. I think there's time for one question. There's one question posted in the chat already. As you increase dimensionality or layer depth, what kind of electron localization are you seeing? Strong, weak, or MOT? How does the lattice of each layer change as you put a layer on top of it and or under it?
Yeah, so I think to answer the first question, it is the strong interaction. Because also this system, they are in the category of what we call the strongly correlated electro systems. So that's when you increase the dimensionality, we have much more stronger electronic interactions. And the second question was, how does the lattice of each layer change as you put a layer on top of it and under it? So
does the lattice get more floppy, or do the atoms become compressed?
Yeah, so if you do thin films, it depends on the substrate you are using, because if the lattice parameter of the substrate is different to the film you put on top, so whether it is large or small, then you have either compressive strain or tensile strains. So that will depend on which substrate you are using for the thin film you put on top. The lattice parameter of the thin films that you are using.
Interesting. Okay, thanks.
Okay. Thank you, Prosper, again so much for your talk.
Yeah.
I think we will break for tea now until 5:15 for the next session. Prosper, if you could just put your email contact details in the chat in case there's anybody else that wants to contact you with follow-up questions.
Yeah, thank you. I will do it. Yeah.
Thank you again, and see everybody in 10 minutes.
Thank you, Kathleen, and then Lawrence. I hope you are ready for the next session.
I am.
All right. Okay. Bye.
So we'll try to start on time. And I see, Auntie, you are here, yes?
Yes, I'm here, yes.
Okay, fantastic. Did I pronounce your name correctly?
Yes, it's on this. It's
Okay. Paul Northrop, I see you are here. Alassane, I see you are here. Divine, I see you are here. Kayla?
Hey, Lawrence.
Hey, how's it going?
Good. How you doing?
Okay. I got a Kayla Hidalgo. I'm sure we'll be here. And I saw Luca earlier. Yep, there you are.
Yes, I'm here.
Okay. All right. I'm gonna...
I am here as well.
Yep, I see you. Yep. Prosper, are you still here? Okay, so it is 15 after the hour. I have we have a few seconds left. And the first speaker is Auntie, right?
Yes.
Hi. So you can share your screen.
Okay, do you see it? We put it in the presentation mode. Do you see my screen now?
Yes, I do.
Okay. Okay. Good afternoon. So my name is Antti Kivimäki, and I work as a beamline manager at the finest beams beamline at Max 4 laboratory in Lund, Sweden. So thank you very much for the invitation to show our recent results here in this meeting. So the outline of my talk is very simple. So I will speak something about the Max 4 laboratory and the finest beams beamline. And the second part of the talk, I will tell about our recent experiments of aerosols that we have been performing at the beamline. So Max 4 laboratory is located in Lund, southern Sweden. This is actually quite close to Copenhagen, so Lund can be reached easily through the Copenhagen International Airport within 1 hour after the flight. What also shows how the laboratory looks from above. So this big circle, of course, is a storage ring, and then this rectangular building on the side of it. There's actually a second storage ring inside. And when we go to the map of the beamlines, so Max 4 has 16 beamlines. They are divided between these two storage rings. The biggest storage ring is 3.0 gigaelectron volt ring made for hard X-rays. And then we have this smaller ring R1 in this building. It has an electron energy of 1.5 gigaelectron volt. And finest beams actually is located in this smaller ring. And the acronym finest beams, it comes from the Finnish-Estonian beamline for atmospheric and material sciences, indicating that this beamline has been mostly funded by Finnish and Estonian research consortiums. This is the optical layout of the beamline. The radiation source is an elliptically polarizing undulator. It has a very long period, 94.2 millimeters, to enable to get photons from very low photon energies of 4.5 electron volts. And then it extends up to soft X-rays until 1,300 electron volts with horizontal polarization. Beamline has 2 branches, but 1 monochromator, so we can make experiments on one of the branches at one time. The monochromator is based on plane grating monochromator using collimated light, and the selection of the branches is then done by putting one of these focusing mirrors M3 on the beam path, so then it deviates the beam to one of the branches. Then we have also refocusing mirror on both branches. Its shape is ellipsoidal, focusing in both directions. At the end of the beamlines, we have the end stations. At one of the branches is a permanently installed solid-state end station for surface science experiments, while in the other branch we are swapping the end station between gas-phase end station and the photoluminescence end station. As I already taught, the beamline starts from 4.5 eV and goes up to 1,300 electron volts. Of course, the photon flux is not very high in all of this range, and all the experiments are not possible, especially in the gas phase at the high energy part of the beamline. Beamline has monochromator has 2 gratings. One of them is working from 4.5 to 50 electron volts, and the total grading with 600 lines per millimeter is started from 15 eV, and then it's going up to 1,300 electron volts. Photon energy resolution of the beamline is reasonably good. The design goal was to have it above 5,000, and this is mostly fulfilled, except at the very lowest photon energies. And for instance, at nitrogen 1 is it's 400 electron volts, we can achieve the resolution of 11,000. So the radiation source is the elliptically polarizing undulator that can provide polarizations of different directions. So typically we are using linear, horizontal, and vertical polarization, and the quality of this light is very good. So the linear polarization degree is practically 1. However, the beamline can also, or the other, they can also provide circular polarized light and ink light, linearly polarized light. And here we get some problems going to lower photon energies because the beamline optics is changing the polarization state of the radiation. But here's an ongoing project that would cancel this effect of the optics. We could run the undulator in such a mode that the light at the end station would be very clean circular polarized light or ink light linear polarized light. And about the end stations, we have 3 of them. So first, autonomous end station. This is used for optical spectroscopy of inorganic materials such as crystals, glasses, ceramics, scintillators, and so on. It can be used to measure emission spectra from 190 to 1,100 nanometers using the optical spectrograph. Then excitation spectra and reflection spectra can be measured in the operation range of the beamline. Sample holder is coupled to closed cycle liquid helium cryostat that allows the temperature of the samples to be varied from 10 Kelvin to 350 Kelvin. So also temperature dependent experiments are possible. And when the storage ring is operated in the single punch mode, then also time result experiment can be done with this end station. The single punch mode is typically used for 2 weeks per year, and then on some single separate days. Recently, the data acquisition system of this end station have been developed so that the 2-dimensional excitation emission maps can be measured. So, like shown in this figure. So every cut of this map, either in the horizontal or vertical direction, it shows emission spectrum, or respectively excitation spectrum of the emission. And there's a huge amount of data can be collected in quite short time. Solid state station is quite complicated setup. As usually it's for surface science, but it's basically composed of 5 different vacuum chambers interconnected via radial distribution chamber that's in the middle of them to transport the samples from, for instance, preparation chamber to the analysis chamber where the experiments are done. The main technique here is electron spectroscopy in 2 different forms, X-ray photon spectroscopy, XPS, and then also angle result photon spectroscopy is possible in this beamline. And then users can also measure X-ray absorption spectra. The preparation chamber has quite versatile sample preparation systems. Sample can be heated and also cooled. Then in the analysis chamber, where the light from the beamline comes, the main instrument is electron spectrometer from SPECS. It has a 2-dimensional delay line detector. It is also equipped with the X-ray tube for times when synchrotron radiation experiments are not possible. And very recently, we are also installing a helium lamp in that chamber. More information about this end station can be found in this instrument paper. It's given here. The third end station that is actually has been used for the experiments that I'm going to describe soon is the gas phase end station. And the main instrument here is has been designed for photoelectron, photoion coincidence spectroscopy. It's usually shortened as a PEPICO. So it is composed of electron spectrometer from Sienta, model R4000, and ion time of flight spectrometer for the detection of ions, and this has momentum imaging capability. These two instruments can be also used separately to measure photoelectron spectra or ion time of flight spectra. In addition, the beamline also has available a magnetic photoelectron spectrometer for multi-electron coincidence spectroscopy. And this can be only used in the single punch mode. We have also set up that is composed of two ion time of flight spectrometers facing one another, and this can be used to measure negative ions in coincidence with positive ions. But in the experiments that I'm going to describe, only the photoelectron spectrometer has been used. So now we go to the second part of the talk. I'm going to speak about aerosol experiments that we performed at the Finance beamline. So why are aerosols important? So it has many aspects that affect our health, life, and technology. So in the health sector, aerosols are the main environmental cause of death. For instance, solid fuel combustion in homes is a main factor that has been very much understudied. And aerosols, they can also spread infectious disease. In the climate sector, aerosols are the main uncertainty in the climate models, and especially aerosols' role in clouds should be determined more carefully. After all, every cloud droplet has started as an aerosol particle. And in the technology sector, use of aerosols enables technological innovation, and we can use materials more effectively with the help of aerosols. Aerosol research has been done at Lund University quite much, but not at Max IV laboratory. So we established a team whose purpose was to develop the in-flight X-ray electron spectroscopy of aerosols to be performed at Max IV laboratory. And our postdoc, Kalle Breger, has been responsible for this project. So I'm basically showing his results. So what is in-flight and why we are doing in-flight XPS? So conventionally, aerosols have been mostly studied when they were deposited on surfaces. However, aerosols, they may undergo some changes on the surfaces. In flight systems, we want to study aerosol particles when they are flying in the vacuum. In their natural form, it's kind of mixture between gas and particles. And studying aerosols with this system, we are still getting information from the surfaces of particles, because XPS is a very surface-sensitive method. So the challenge of this kind of experiment is to bring aerosol sample from the atmospheric pressure to the vacuum so that we have enough particles in the beam, particle beams for the measurements of the XPS spectrum. However, this is not the first time that it's been done. So there have been some systems that have been developed at other facilities. They are given here on the references. So we, of course, studied them more very carefully before designing our system. And generally, critical components of this kind of system or delivery setups are critical orifice through which the artificial beam is going through, and then dynamic lens that was bought from Iodine Research Inc. So ready product, it's basically is composed of successive apertures of decreasing diameter, and its effect is to collimate the particle beam in a very narrow beam that can be then brought through skimmers to the end station, and then where it crosses the photon beam. Here is the drawing how the setup looks. So the artificial beam is brought to the system through a valve, and then it goes to the tube that is at the end of which is the aerodynamic lens, ADL, shown in this picture. A particle beam that is coming through the lens is going through skimmers, and then it's going to the gas phase end station, which is part of the Funny Beams beamline. So we have the option of using 1 or 2 skimmers. So in the first beam time we tried 2 skimmers, but the alignment was so difficult that we directly took away the first one of the skimmers, and so we have been after that running the system with only 1 skimmer, and it's perfectly possible. So in the source chamber, the pressure is in the range of 10 to minus 3 millibars, and then in the gas phase end station, where the experiments are done, then we have the pressure in the low 10 to minus 6 millibar range using only one skimmer. So the most experiments, at least this second skimmer is not needed. And here is the photograph of the setup, how it looks at the beamline. And here is Kalle Breger, the postdoc who has been responsible for this development. So artificial delivery system is shown here. Here's the manipulator. Here is the source chamber pump by a big turbo pump. And the skimmers here in this very close to the interaction region. So, and electron spectrometer is placed in the vertical direction. So the electrons are collected in this direction and analyzed with hemispherical analyzer. When the setup was used first for the measurements of artificial solutions, so this is basically the experiment setup. So we are making some sample generation system here, which is creating the articles and then leading them to the sample delivery system. So in the case of solutions, we have atomizer, so we are putting nitrogen gas in the sample solution, and then articles are connected to this pipe, and they are going through the dryer. Some of them are going to the experiment where they are measured, and some of them are going to the device that measures the number size distribution of the particles that we are measuring. So we get the idea how big these particles are. And here are some experiments we have been performing of different salts. We are calling these sea salts. So here we measured sodium chloride, sodium sulfate, ammonium sulfate, and ammonium chloride. So in each of the components, we could see the constituent atom signals. For some chlorine 2p and sodium 12s. We also monitored the signal from carbon 1s and silicon 2p in order to see if there was some contamination from the previous samples or from the tubes themselves, but the signal from them were negligible. And in this figure, we can see the size distribution of the particles for these articles, and so the typical size is between 50 and 100 nanometers. We have also measured answers from the mixture of solutions. So in this experiments, sodium chloride and ammonium sulfate were mixed together in different concentrations. In the experiments, we also varied the relative humidity of the samples. And according to thermodynamics, it is actually expected that the chlorine ions would evaporate and form hydrogen chloride gas during aerosol generation and drying. And mostly so if the relative humidity is low or the particle mass concentration is low. And we could actually confirm this kind of expectation. So we can see that the gas signal that is here at the different binding is than the particle signal, its intensity increases when the relative humidity is decreased, and it is also bigger when the particle mass concentration was lower. So here to get this hydrogen chloride gas, actually we need to get hydrogen from this ammonium sulfide and the chloride from sodium chloride. So they are undergoing some chemical reaction. So this setup have also been used to measure nanoparticles from metals. Users or collaborators from the Lund University brought their sample generation system to the beamline. It is based on spark ablation of metal electrodes. I don't exactly know how this works, but it worked quite well because we could really see nanoparticles using this setup. And here it is shown at the beamline. So this was the spark ablation generator. And then when nanoparticles were mixed with the nitrogen gas, some of them were brought to the system and some to the atomic aerosol mass spectrometer, so we could measure nanoparticles from different metals. Here are some results that we obtained from different metals, aluminium, tin, copper, and zinc. There are also some other metals that we studied. So these experiments were a little bit more difficult than those of the salt aerosols. So there are some limits with correlates we can study. For instance, tin 3D, there were some data about it in the literature, but we could not get any signal because the photon energy would have been more than 500 electron volts. Instead, we got very good signal from tin 4D level that has a quite low binding energy. However, also very low binding energy levels cannot be studied because we have the carrier gas nitrogen that is giving very high signal in the valence photonization. So this setup has been working very well, and so we decided to give it available to the users. And first user experiments were performed last month at Finest Beams. So here is a photo of one of the experiments. Here, users, they actually brought a burner to the beamline and studied open flame. So this was the first open flame experiment on Wax 4. And they sampled combustion products by placing a small tube with a small orifice in the flame, and then nitrogen gas was pumped through the system, and it was bringing products to our setup, which could be measured. I don't have any pictures because these results belong to the users. However, carbon 1s photoreference vector could be measured from these experiments at the photon energy of 350 electron volts, and the experiments were quite successful. So this is the status at the moment. So I can come to the conclusions. So Finest Beams beamline has been in operation since 2019, and it has shown quite good performance. It operates in very wide photon energy range. End stations are in user operation. And aerosol science is a new research area that we have been doing at Harness Beams. So we have developed this aerosol sample derivative system and commissioned at the gas phase end station. It's working quite well. At least measurements up to the carbon 1s edge are possible. And the setup is already available to general users since this autumn. And users also can couple this system with their own particle generation sources. So very many different kind of experiments can be done with this setup. And I want to thank my colleagues at the finest beamline, Kirill Chernenko, Benjamin Wang, Kalle Breger, and Mirza Kalsami. I also want to thank people who have participated in the aerosol experiments, and most of all Kalle Breger. So these are his results, and he has been very good postdoc, and thanks to him, this project has been carried out successfully. Funding for the beamline has come from Estonia and Finland, and I also want to thank our funding collaborators. And thank you very much for your attention.
Thank you. Very nice talk, very nice beamline. Are there any questions for the author, for the speaker?
Yeah, if I can.
Yep.
Yeah, so also from my side, very nice talk. I was wondering of some of the really topical, contentious things, seeing as you have the capacity to look at chemistry in lower pressure. Things like the driving of climate change, maybe in the upper atmosphere with trace elements, or with the flux of radiation from the sun, like the cloud experiment at CERN, or something similar, where you can get a view of that and look at additional mechanisms that drive heating or cooling, from the upper atmosphere, with the climate change aspects.
Yeah, such research has not been done, even though the name of the beamline hints at atmospheric research. But maybe something that is maybe a little bit related is that we can study these negative ions that obviously are of atmospheric or astronomical importance also. So this kind of experiment has been conducted for some samples. Now, of course, the beamline itself is, because it's covering the photon energy from 4.5 eV upwards, then it could model to a certain extent the solar radiation. So, but we are doing experiments what our users are wanting to do. So basically, there has not been direct atmospheric interest in our beamline.
Okay.
It's more.
Thank you, but I think it will be very useful for that, in the future.
Yeah, I hope that. Yeah.
And do you have experiments in the liquid phase?
Yeah, it is possible to put liquid jet at the beamline also, and actually such experiments have been done previously.
Okay.
So we can measure XPS from the liquids. So this is possible. However, there's another beam at the Max 4 laboratory where that setup is working better. So we are a bit dividing our fields, but such experiments are possible. Yes.
Yeah. Okay. Well, that's interesting because there's a old problem called the Mpiba effect, which is named after this Tanzanian student a long time ago, about why does hot water freeze faster than cold water. Have you ever heard of this experiment?
No, I haven't heard about it, but yeah.
Yeah, it's still unsolved. But it was something that actually was a young student, a learner, observed many years ago in Tanzania. Somehow he was putting in the refrigerator warm water, and he noticed that it freezes faster than when he puts cold water in. And there's been a lot of theories about why that is. I'll write to you about it.
Okay, it sounds interesting, really.
Yeah. Okay, well, let's thank the speaker. We go into reactions. We can do a hand clap. You can do a thumbs up. And thanks again. And then we can go on to the next speaker. Excuse me. Who is Paul Northrop.
Good morning or afternoon, depending on where you are.
Depending on where you are, yeah.
It's morning for me.
Start date.
Yes. So I will share my screen here. Oops.
Nice picture in the background.
Oh, thank you. My sister, actually. Okay. So do you all see my screen?
Yes.
Yes.
Okay.
Yes.
So today I will be talking to you about exploring the grain scale chemistry of African meteorites using synchrotron X-ray fluorescence microprobes. And this is work done primarily at NSLS2 at the hard and tender X-ray microprobe beamlines. Okay. So African meteorites actually form a very large fraction of all known meteorites. Meteoritical Bulletin database describes about 15,000 African sourced meteorites. And these include a variety of meteorite types, including carbonaceous chondrites and Martian and lunar meteorites. And the study of these, particularly at the grain scale, often utilizes synchrotron microprobes, which are a versatile and element-specific tool for studying microscale heterogeneous materials such as these. In particular, X-ray fluorescence imaging gives us the two-dimensional and sometimes three-dimensional distributions of elements and the correlations between them, and tells us a lot about the chemical and physical history of samples. In parallel with that, using X-ray absorption spectroscopy at microscale resolution can also identify by XANES or the near edge structure of the spectra, identify the oxidation state and fingerprint specific chemical species in a sample. And extended spectroscopy, or XAFS, can tell us more about the local structure within about 10 angstroms of the element of interest in both crystalline or non-crystalline materials. Microprobes also often have accessory microbeam X-ray diffraction capabilities, which also help to identify crystalline phases. As I said, they're very versatile, typically offering micron to submicron scale spatial resolution and field of view up to more than 10 millimeters in some cases. They're typically divided into more standard hard X-ray microprobes operating at 5 kilovolt and higher, which are excellent for transition metals and heavier elements, while beamlines specialized in the tender energy range, 1 to 5 kilovolt roughly, access lighter elements that are very important, such as magnesium through calcium. And these techniques are all generally non-destructive and require minimal sample preparation. Ideally, just a flat surface or even a mostly flat surface will suffice. And they're measured in air or at low energies in the helium atmosphere, so no vacuum or anything particularly invasive to the samples. So they're generally non-destructive. You do have to be careful in some cases of beam-induced chemical changes, but those are things we keep track of. They're not that serious. So the first example is a carbonaceous chondrite. This is Northwest Africa 12748. It's the designation of that. Its composition in chemistry actually represents some of the earliest material from the early solar system, and it has not been affected by planetary formation processes. So this preserves some very, very old material from the early solar system. It also records some early chemical processes that occurred in small bodies and asteroids in that time frame, when things were still at somewhat active temperatures and processes were ongoing to a certain extent. These meteorites like this one also contain abundant prebiotic organic compounds, which are very interesting. And they also contain nutrients such as phosphorus and sulfur that are essential for the development of life on early Earth and potentially Mars or elsewhere. So these are very interesting and informative materials. And they're also very heterogeneous. As shown in the maps on the bottom here, the lower left map shows a cross-section of the entire meteorite, which is about 12 millimeters across. It's depicted in 3 colors. So chromium is shown in red, iron is shown in green, and nickel is shown in blue. And you see quite a bit of heterogeneity in the chemistry of those elements. Looking at the indicated area in close-up on the right, and I think I'm just move this here. Okay. So on the right, this image is at much higher spatial resolution, and it shows calcium in red, sulfur in green, and chromium in blue. And again, you see quite a variety of chemistry on the grain scale down to the micron level. Now, seem to be having a little trouble with my screen here. Okay, so continuing with this meteorite, we can use the Zanes at any given pixel of the map to explore the chemistry and speciation of particular elements. So in this case, in the center of the screen, the upper plot is sulfur Zanes of selected pixels in the maps. And they show sulfate species in some locations, indicated by the tall peak at higher energy, as well as sulfide species, which show up at a lower energy for the absorption edge. And if you look closely at that, there are several different sulfide species that can be distinguished in different places in this sample. Similarly, the bottom plot is phosphorus Zanes. And this again shows different locations having phosphate or phosphide species. Now, armed with this information, we can then go back to the mapping mode and set the incident beam energy at an energy that corresponds to a particular feature of a particular species of element. And so we can map, for example, on the left here, sulfide versus sulfate species in an area of the sample. And so sulfide is shown in red and sulfate is shown in green. Most of the sulfur in the sample is in the form of sulfide, but there are definitely spots of sulfate. And you also see that there are some yellow to orange shadings on many of the sulfide grains, and that indicates a partial oxidation to sulfate, or a mixture of the two species. Likewise, phosphorus is also found in this sample in both phosphate and phosphide species. The map at right shows the phosphide in red and the phosphate in green. And the yellow spots are places where there are both species together. So this map was done at 4 micron resolution. So there's a lot of interesting chemistry going on. And it's clear that the chemical reactions that form the different chemical species in this particular sample did not go to completion. There's partial oxidation and other intermediate types of chemistry that indicate that the processes did not go to equilibrium, but were an ongoing process for a time in the history of the sample. And that can tell us a lot about the origins and the processes that happened in the early solar system. So these are very interesting materials. Switching gears to a different meteorite. This is another Northwest Africa meteorite, but it's a Martian meteorite. So it is a piece of crystalline bedrock that was ejected from Mars in a large asteroid impact or some similar event and found its way to Earth. As such, it is heavily shocked, likely from that impact, but it is one of the few pieces of material that we have on hand that we can actually study in the laboratory that is from Mars. And so that's a very important and valuable sample for a study of Mars. In this case, the calcium zanes is shown on the right, and the three spectra indicate three different minerals. The upper one identified pyroxene, so it's calcium and pyroxene. The middle one is apatite, so that's a calcium phosphate. And so in the map at left, the yellow grains are apatite grains. And the bottom spectrum of the calcium zanes is calcite, which is the bright lighter color red grains in the sample. That's a different mineral. And the calcite, it turns out, is from terrestrial contamination after the meteorite landed on Earth. And so we have to be careful about the history of the sample after its arrival as well as before its arrival. Because the calcite, some calcite was deposited in pores in the sample after it landed on Earth. Taking a closer look at this sample, we see that the pyroxene grains are these long, large grains. They are zoned crystals, so the core of the crystal has a lower calcium content than the outer part of the crystal, which tells us a bit of the crystallization history of the original igneous rock. And the fluorapatite crystals are shown in the yellow on the upper image and red in the lower image, and they show evidence of being heavily shocked. The blue to purple areas in the upper image have the composition of feldspar, so calcium, potassium, aluminum, silicate, but they are amorphous. They have been shock melted in this process. And the potassium and calcium zanes identifies the amorphous structure as opposed to the crystalline structure for this material. So again, it's the combination of zanes and imaging that really tells the whole story. In the lower image, the bright green spot there is a troilite or iron sulfide grain. So that's present in this rock as well. For comparison, there's a different Martian meteorite, another Northwest Africa meteorite, that is more of a surface rock rather than a deep igneous bedrock, and it's not as heavily shocked. So it was a smaller magnitude impact that ejected it from the surface of Mars. And so it potentially preserves more of the Martian history and less of the impact history of it. And in this case, it's phosphorus, sulfur, and aluminum shown here. And it also contains apatite crystals shown in red, and also iron sulfide shown in green. But in this case, the apatite is a chlorapatite as opposed to a fluorapatite. And the iron sulfide is a pyrite or FeS2 rather than a troilite FeS. And so this indicates that this rock has been subjected to hydrothermal alteration while on Mars. And so that tells us a lot about the near subsurface geochemical processes that have occurred on Mars. And it's an interesting probe of that process. So there's a lot of information to be gleaned from these samples, but you do have to be aware of the complex history of them. It'd be much better to be able to actually get pristine samples delivered back here of our own choosing, but we'll take what we can get for now. The third example is a lunar meteorite, which is a piece of from the moon. It's a basaltic rock, and it also has small fluorapatites in it and small troilite grains. So we can explore the chemistry of the lunar basalts by study of this meteorite. In this case, the apatite was identified by phosphorus zanes. So in summary, meteorites carry a wealth of information about places and times past that are otherwise not accessible. And that information is encoded in the microscale and grain scale chemistry and geometry of the sample itself. And synchrotron microprobes are ideal non-invasive tools to conduct this grain scale characterization of extraterrestrial materials. And particularly using both hard X-ray and tender energy beamlines to access the full range of elements of interest. And of course, correlated measurements with other techniques can also be made using a micro or nano scale, infrared, Raman, etc. And ultimately, if there are things identified in the samples by these non-destructive techniques that need study by mass spectrometry or more destructive analyses, then you can use the non-destructive techniques to guide and prepare for the best use of the more destructive techniques and preserve as much of the sample as possible. So that's my presentation. I'd like to thank the conference organizers for this opportunity, NASA for its funding, and the particular beamlines at NSLS2, and a variety of collaborators and contributors. Thank you.
Thank you for a very nice talk. Are there any questions for the speaker?
Yeah, I also really enjoyed the talk. I was wondering, did you ever find diamond-like carbon or diamond itself or lonsdaleite, something similar in these meteorites?
I believe that diamond has been found in some of these meteorites. What I presented was did not include carbon as a very light element. So these techniques are best for magnesium and heavier elements. For carbon and lighter elements like oxygen and nitrogen as well, Sticksom techniques are usually used. So I have not actually gone into that. That's certainly a complementary technique. The sample preparation is somewhat different. But that would, so a Sticksom or fluorescence probe at the carbon energy would be necessary for that study. That is also very interesting.
Yeah, okay, thank you.
Okay, let's thank the speaker. There are no other questions. You can, or if you have more questions, you can put them in the chat. But let's give a hand clap and a thumbs up to the speaker.
Thank you.
And the next speaker is Alassane Traore. And you're unmuted, but you can share your screen.
Okay. Hi, everybody. Do you hear me?
Yes.
Okay. As well, do you see my screen?
Yeah, you see.
Yeah. Okay. Thank you very much. So before starting my talk today, I would like to thank the organizing committee with this joint virtual event of the African Light Source and the African Physical Society. So I'm very happy to to be part of this audience and to take this opportunity to give a talk about the last results we got regarding collaboration we have with different facility around the world. So my talk today will be based on instrumentation, neutron activation analysis, and the proton-induced X-ray emission techniques, supported with robust statistics to try to give an overview of rare earth macro and micro element correlation regarding very scarce type of rice, which is named Glaberrima. This rice is cultivated in Senegal, in two different parts of the country, in the northern part and in the southern part. And to start my presentation, we need to share with you what was the motivation of this study. At the beginning, we were looking for the bioaccumulation and the transport mechanism regarding this special rice, because it is the only rice we have in Africa which is endangered, and this rice have more than 3,500 years old, and it was cultivated in the past in one area we called Delta of Niger, and this Delta of Niger is now named Mali. And from this region, everything started, and this was spread around across around the world, and it was very special rice because based on the climate change, the yield of the rice was not ready to change, and some of the transportation of bioaccumulation, transportation of macro element was not affected by special condition like salinity, like acidity, and a big amount of phosphorus. So the second motivation is to determine a kind of translocation factor, because as you might know, in my country, we are using a lot of fertilizer, more than 1 million liters of fertilizer a year from one area to another. And with this study, we were looking to see how to optimize the use of fertilizer based on the absorption of some element which are mostly present on soil or water, and which are very essential for nutrition aspect on the seed. So we will see at the end of my presentation one table which are showing the translocation factor we have found based of this study. And last but not least, we try to evaluate the suitability of this type of rice regarding a certain amount of tolerance in the on water and use of fertilizer and the salt. So to do this study, we have to prepare our sample, and for preparing this plant material, we need to collect different type of trial, and for this different type of trial, 2 were assigned, and the first one is what we call the trial 317, and for this trial we give an amount of salt and an amount of water, and in the control area, and we perform the same protocol for the second trial, which is called 330, and for these 2 trials we perform a kind of let's say crop control. At the beginning we have to collect the vegetative rice. 2 months later, we collect a second batch, and at the maturation set, we do the same. So we have 3 types of samples regarding their maturation in the control area. So to do so, we need to prepare our sample because we are looking plant material, and for plant material, we always need to be careful about the sample preparation. So different conditions were used to prepare the sample, starting from the selection in the field to the preparation in the laboratory using freeze dry. We were able to prepare a certain amount of condition of samples in the laboratory in Czech Republic at the Nuclear Physics Institute. And from this laboratory, we were able to do what we call bulk analysis and a 2D dimension imaging to see how we can perform distribution of element from plant. And we have used two different type of techniques, proton induced X-ray emission and instrumentation neutron activation analysis. So two different techniques were used, and from these techniques we were able to show up for the leaves, for example, a kind of distribution of element that regarding the targeted element. We were looking for titanium, iron, bromine, and some rare earth element to see what could be the distribution of this element to correlate with the use of this element to combat stress or excess of salt or excess of water. So this picture show kind of demonstrate how complex is the matter to see the correlation from the roots to the grain through the seed, the stem and the leaves, and we have tried to build a kind of model based on machine learning to see how we can stabilize one model which is based on the measurement and the condition we have fixed in the yield, and to stabilize this model using different techniques and different conditions to see how this model will fit in certain manner to better understand the absorption level of element within plant tissue. So these figures show a kind of correlation regarding rare earth element in this part of the figures, and with macro element like calcium or potassium or scandium or iron, and to see how we can drive to a certain manner to stabilize the amount of this macro element in soil, and to predict the same amount in seed or in leaves. So we were able to have a very nice results on the model to predict such kind of, for some element, how we can predict the amount in seed by looking only the concentration of different element correlate with rare earth element on soil and in different parts of the plant. So we have built a kind of heat map because we were looking to see from root to grain for these three different type of sample, what could be the effect of the environmental condition, and to see in which part of the measurement we can see good correlation between chlorine, sodium, and others element with rare earth element you can see on the right part of these figures. Donc the same work was done with the last different, the two remain sample, and we can see from environmental condition the correlation is changing based on the specificity we can see from this rice plant. So based on the results we have got, we were able to give a clear, let's say, overview on the next step regarding the accumulation of element within tissue, a preliminary mechanism we have to validate using the model we have built, and as well to see how we can compartmentalize from cellular tissue and different level of stage of maturity from the plant, how we can assess some hazardous element like mercury, arsenic, cadmium, and chlorine. So based on these three remarks, we were able to give a very nice clear overview of spatial investigation of toxic element, and to use the 2D imaging to be able to have what we call a macro-analytical imaging techniques. And from these figures, we were able to give more information about the metabolic process, about the influence of different soil composition, and the genotype response, because we have used 3 different types of rice regarding condition and maturity and genotype. So I have this table, which is a summary of all the results we have got regarding let's say the level of element in leaves and in roots. And from these figures, we were able to build what we call a translocation factor, which can be shared with the cultivator. And from this translocation factor, we were able to advise to the farmer not to use fertilizer with higher content of phosphorus, potassium, or nitrogen, because this translocation factor will tell us whether or not, with the real amount on soil or water, we will have sufficient amount in rice in seed. So these results were published in Nuclear Instrumentation Method B, Research B. And from these results, we have the opportunity to get another grant from LAMP. And we have to thank LAMP for this grant, because we will move with one collaborator like Canadian Light Source to perform complementary measurement to validate our models, and also to get another information regarding different type of condition we have performed here in Senegal in what we call African Rice Center. So I'm not going to talk more than that. I would like to thank you all these audience for your kind attention. Thank you.
Thank you. That's a very nice talk, very nice results, and very important. I think we are trying to stay on schedule. If anyone has any questions, you can put them in the chat, or if you have a quickie, we could entertain just one. So why don't we move on to Divine Kuma, who is from Duke University in the United States. You can share your screen. There you go.
Okay, can you see my screen?
Yes.
Okay, awesome. Well, thank you very much for the kind opportunity to talk, give a talk. My name is Divine Kuma. I'm currently an associate professor in the physics department here at Duke University. And I've been a long-time user of synchrotrons to study low-dimensional materials. So I'm going to talk a little bit about some of the work we do and some of the applications of synchrotron sources for studying low-dimensional quantum materials. So I'm going to be talking about inorganic materials, which have potential, where we're trying to understand collective effects like superconductivity and magnetism by using these synchrotrons to really peer down at the atomic scale structures of these systems. So my talk today is going to be focusing on synthesis, how we can grow some of these materials which have to have the very specific crystal structures, and how we can grow these materials with thicknesses on the order of a few atomic layers and make heterostructures, multi-layers, where interactions at these interfaces can lead to very interesting new applicable quantum systems. So I'm going to focus on a particular material, or titanium monoxide, where we can stabilize a monoclinic phase. And I'm going to show that we can use in situ synchrotron characterization, where we grow this material and at the same time use synchrotron X-rays to characterize the structure as we are growing this material to stabilize a very unique phase of this system. So very quickly, nature gives us the periodic table of elements. We know we can separate them by some of their characteristics. But if we take any element in this particular periodic table, for example, if we take carbon, the actual physical properties depend on how the atoms are arranged in the system. So if you have diamond has this nice shiny properties. It's hard because of the way the atoms are arranged at the atomic scale, where the carbon atoms form this diamond structure, which gives us this expensive diamond, beautiful crystal. If these same carbon atoms arrange themselves in this hexagonal lattice, which are weakly bonded, we get graphite. And even though these are both carbon, if you try to give a gift as to someone as graphite instead of diamond, they might not be too happy. But more interestingly, if we take a sheet of this hexagonal carbon lattice and we form something called graphene, it turns out to be very, very interesting because it's superconducting. If you apply a magnetic field and measure its resistivity at low temperatures, you can see these plateaus, which are really, really interesting as for physicists to study. And people are even thinking of starting to think of devices you can make based on these very, really thin sheets of carbon atoms in making quantum-based devices. Right, so my interest in studying quantum materials is trying to understand the collective behavior of systems. So collective behavior, referring to things like superconductivity and magnetism. And again, the idea of the reason we need synchrotrons for a lot of these very thin materials is that synchrotrons provide very high intensities, which allow us to get really good high resolution images and information about these systems. So in a lot of these phases, some of the things we like to understand are the transport properties, their electric and magnetic properties, and how they are correlated with the structural properties of these really thin materials. And there are a whole range of applications, from making good sensors, good fuel, good cells, and making new high TC superconductors, but also making devices like devices where you can rely on the spin of the electron in the system rather than the charge current, so that you can make devices which use less energy and are more efficient. Right, so in my group, we grow these materials because we are interested in the atomic limit. Rather than making bulk crystals, we're interested in making atomic layers of these materials. And the technique we use allows us to build the systems from the ground up. So we're starting off with a very thin layer and we're making these multi-layers. And the technique we employ is called molecular beam epitaxy. So we can, in this ultra-high vacuum system, so the base pressure in this system here is on the order of 10 to the minus 10 torr. We can evaporate different high purity elements. We can calibrate their fluxes. And as the flux of these materials we evaporate land on a single crystal surface. So this is what I'm referring to as the substrate here. They condense and they form a crystal structure which mimics the atomic layer pattern on the substrate. So here we can create crystal structures which do not exist in nature. And a lot of these are predicted by theory. And we can also combine these materials in these multi-layer stacks very precisely to produce new and interesting effects. So this is a picture of what the system looks like. A lot of the steel here is just pumps to evacuate the system. At the bottom, you have the fusion cells. But in situ, during the growth, if we're doing this in the lab, we only have very few tools to actually know exactly what we are growing. So in here, we have an electron beam which hits the surface, gets diffracted. We can look at the diffraction pattern, and it tells us about the symmetry, about a little bit about how the atoms are arranged on the surface, but we don't have any information about the chemistry or what's going on below the surface. We can take our samples out, we can thin them down, make them a few microns thick, shoot electrons through them, and get these really beautiful electron microscope images in transmission, which allows us to tell that our material is nice and ordered. So each of these white dots you see here is a column of atoms. And we can also get chemical information in these electron microscope techniques. But this is a destructive technique. In many cases, we like to know what is happening to our sample in 3 dimensions as we grow the material and also as we operate the system. So the technique that we employ at synchrotrons for these thin films allows us, involves measuring diffraction information and converting that information into these 3-dimensional electron density maps where we can resolve the position of the atoms in our material in 3 dimensions with sub-angstrom, sub-picometer resolution. And so because my topic is on superconductivity, part of the reason in studying superconducting materials, especially thin films, is that there's a lot of interest in understanding why some materials have zero resistance at below some critical temperature. And if we can understand that, then we can design new materials which also do that at room temperature, and then that will lead to significant reduction in power losses, for instance, and more energy efficient devices. So the high TC cuprates were discovered in the late 80s. There were some Nobel Prizes awarded for that. For these materials, without applying pressure, some of the highest temperatures people have obtained are close to 100 Kelvin. Ideally, the pipe dream is to discover materials which do this at room temperature, but by understanding how this happens at these low temperatures, we can design new interesting materials. But in studying, there's been a lot of studies in these materials which have found out that the superconducting properties really are sensitive to the atomic displacement at the picometer scale. All right, let me redo this. Can you see my screen?
Yes.
Okay, all right. So again, there's a disconnect between growing the material, doing all the characterization, and then taking it to a synchrotron. And so we'd like to close that loop by doing a lot of this all together at a synchrotron. So the synchrotron sources we use are the advanced light source and the advanced photon source. And the kind of experiments you can do at a synchrotron include diffraction, where you can get information about the structure. You can do spectroscopy because these synchrotrons allow you to tune the energies of the X-rays at these facilities. And so you can do spectroscopy, element-specific, get element-specific information. You can also do imaging where you can shoot X-rays, look at the transmission. And in this work here, I'm showing we're able to, for example, look at the distribution of elements in a nickel-based superalloy, which is used in turbine engines in hydroelectric dams. So this is just a schematic of the experiments we do. We rotate our sample with respect to the beam. We measure diffraction in 3 dimensions in reciprocal space. We convert that into these 3D maps, and then we can determine the structures and then correlate these structures with some functional properties. So to close the loop, we started doing these measurements at some of the beam lines where you can actually grow the material. So there's an MBE system at the beam line, and you can grow the material and do X-ray diffraction as you're growing the system. So this work here, we've been doing at a 33 IDE beam line at the advanced photon source. AfPS is currently being upgraded, and so there are going to be more of these facilities and these opportunities available in the future. In the case of titanium oxide, in most of these superconductors at high temperatures, they are metallic, and then because the resistance goes down, and at some finite temperature, the resistance drops to 0. In a lot of these titanium oxide systems, we find out that the resistance actually goes up before it drops to 0, and we try to understand what how this transition occurs and why it occurs. And in many cases, it's due to disorder because you can have multiple phases of this system present. or vacancies which are randomly distributed. And so we wanted to use this X-ray technique to determine first XC2. So in this picture, I'm just showing all the different possible phases you can get, and the fact that we can tune them by tuning the thickness and the amount of oxygen we have during the growth. So we use this in situ technique to optimize the growth to determine to get the particular phase. And the particular phase we're after was one where you have titanium and oxygen vacancies present, but these vacancies are ordered throughout your entire sample. So having these ordered vacancies allows you to have less disorder in the system. And we do find that in this case, we end up, rather than having an insulator to superconducting transition, the material is metallic at high temperatures and then starts to superconduct at around 3.5 Kelvin. All right, so I made this presentation just to give a really quick overview, but the whole motivation here is to point out that in developing this synchrotron X-ray facilities, there's also the possibility of having in situ techniques and growth techniques online, which can be used for studying how materials grow and for creating new materials. But in a lot of cases, some of these synthesis techniques, which are complex and expensive, if they're situated at these beamlines, can also serve as shared facilities where they can be, users can come to the beamline with some material they want to grow, and they can do this even while the X-rays are off, and optimize the growth and then perform the in situ measurements. And having some of these cluster tools where you can do both growth, synchrotron X-ray characterization, angle resolve photoelectron spectroscopy, like previous speaker had talked about, can allow us to accelerate the discovery of very important and critical materials with a wide range of applications. So just in the interest of time, I would like to stop here and take any questions.
Thank you, Divine. Are there any questions for the presenter? Well, to stay on time, if you have questions, let's just deposit those into the chat. And let's just move on to the next speaker. Are we, yep, we're about on time. Kayla, are you here? I thought I saw her earlier. I thought Kayla was here earlier.
I could always talk some more. I'm joking.
Well, just quickly, so when you moved your lab from NC State to Duke, how much equipment moving did that involve? And did you have to realign optical tables and stuff like that?
So the main instruments we have are the deposition systems, so the MBE systems. So those do not involve any lasers or any alignment. So those are relatively simpler to get going again. What we are starting to do now is we now have in situ AfPS, X-ray photoelectron spectroscopy, and AfPS capabilities, so that we can grow the materials, and without taking them out into vacuum, we can look at the electronic, do some electronic characterization, both here, and then if we have to go do this experiment as synchrotrons, we've already optimized a lot of the conditions before this experiment up.
Okay. So I don't see Kayla, but I swore I saw her in the chat, in the Zoom room here earlier. Why don't we do this? I see that Lucia is here, right?
Yes, I'm here.
Why don't we proceed with your talk, and then I will send Kayla an email saying that, hoping that she's okay, and that
just sent her. I sent her an email. So
okay, so yeah, send her an email and just we're just going to swap time slots if that's at all possible. Is that sound like a good
Yeah,
idea?
yeah, that's fine. The problem is just all these time zones are just hopping all over the place. That's the problem, I'm sure.
Yeah, you won't believe what happened
You
yesterday in the
know.
AfPS session. I guess you would believe it. You
So
mess
just
up a
proceed.
time zone, you could be 4 hours late.
Yeah, so Lucia could just go on and do her
Yeah.
presentation.
Okay.
So can I start the sharing?
Yes.
Can you see my screen?
Yes.
Okay. So I'm Lucia Zuin. I'm the beamline responsible for a VUV soft X-ray beamline at the Canadian light source. I'm also the CLS lamp liaison, so I will touch base also on that. And do you see in presentation mode?
No, it's that I need to switch to presentation mode.
Yeah, okay, better now?
No.
No?
Did not switch that. Share your screen again.
Just this.
And then the presentation mode down at the bottom.
Yeah.
A little slow going there.
Is going.
Maybe there's that. What's that button at the top?
Okay, let me try like that. No, it's giving me an error. Can you see like that?
Yep. No.
Do we have your presentation? Did you send it to us?
Yes. I uploaded the presentation yesterday.
Okay, so why don't you get the presentation then, Lawrence, and you can just show the slides.
Okay, let me find it. Presentation materials, yes. Okay, I'm downloading it.
Well, I will keep talking while you download. So as I said, I'm the beamline scientist for the VLS PGM beamline. It's a VUV soft X-ray beamline at the Canadian light source. The Canadian light source is quite a mature facility. In a couple of years, it will be 20 years that we have become operational. It's a relatively small ring because it's only a 171 meter circumference ring, operate at 2.9 giga electron volt, and we operate in top-up mode at 220 milliamps. And
okay, and then
okay, perfect.
Does that work?
Yeah.
Okay.
Yeah. So can you?
There's a mode here. No screens. And
it may be a PDF. Is that a PDF? I mean, we can see it.
It's a PowerPoint, but
Yeah, I'm
So
trying to. What's the mode that does the subtitles? That's the one I'm
That's
trying
fine. That's fine the way it is now.
to. Okay.
Bigger, we can read it.
Okay.
okay,
So I'll go back to
so
slide 1.
no, you can go on slide 2.
Slide 2. Okay. Here I am.
Thank you. Yeah. So 22 beamline on an 171 meter circumference ring. All the straight have been used now. And the VLS PGM beamline, it's actually in the lower energy part of the ring. We cover between 15 up to 250 electron volt, therefore below the carbon edge. The Canadian light source has many synchrotron cover different technique. You can see on the right-hand side of the screen, we go from imaging, spectroscopy, diffraction, and microfabrication. Few years ago, all the beamline were divided into different pillars that depending from the majority of the user that use those specific beamline. So we have the health group, the environmental group, the advanced material group. Historically, beamline like VLS PGM will be grouped with advanced material because from also the talk that we hear today, it's where a lot of AfPS, AfPS or gas phase technique and user, the energy that are most used for this kind of things. VLS PGM is kind of unique in a sense because the majority of the users come from agriculture and environmental sector. So if we go to the next slide, agriculture is a pillars. Can we go on the next slide?
Next slide again. Okay.
Yes, please. No, the other.
3. Yep. Okay.
Okay, so why agriculture as a pillars for the Canadian light source? So it's in Canada, there are 4.3 acres per capita of arable land. Now, the Canadian light source is that little red star that you can see on the bottom left-hand side of the screen. And Saskatchewan, the province where the Canadian light source is, has more, in Saskatchewan, there is more than 40% of Canada arable land. The university in Saskatchewan has 2 very strong departments, so the soil science department and the agriculture department. Therefore, trying to increase the use of the synchrotron for this type of relatively young user, because there are agriculture users using a synchrotron is something that is has been happening just in the recent years. It did make sense for the CLS. So if we go to the following slide, you can see that in 2019, the Canadian light source, together with CHESS, the synchrotron at Cornell, and Sirius, the synchrotron, the Brazilian synchrotron light source, decided to start this Pan America light sources for agriculture. The very first conference was hosted in Saskatoon in 2019. Following 2 years later, we were in the middle of a pandemic. Therefore, Sirius organized a virtual conference. And just July of this year, we had an hybrid conference organized by CHESS, where there was some that were coming virtually and some other that were in person. So if we go to the following slide. So about VLS PGM. So we can do X-ray absorption spectroscopy on element that are quite important from environmental and agriculture point of view. So we can cover sulfur, phosphor, silicon, aluminium edges, and also we can cover the boron K edge as well as the lithium K edge. You can see from the picture of the beamline that we have glove boxes installed to the beamline, and that is specifically for when we are doing a more material-related study or energy-related study like battery, etc., at the lithium K edge. We have 2 branches. At the end of each branches, we have an station that can perform, that focus just on X-ray absorption spectroscopy. One with a larger spot size and the other with a smaller spot size. The photon flux is over the entire range of the beamline above 10 to the 12 photon and per second, while we can go higher than 10 to the 13, specifically in the 120-200 electron volt region. That is exactly where phosphor, sulfur, and boron are sitting. As I said, the technique we do XIS, we have a total fluorescence yield. We can collect the total fluorescence yield over the full energy range of the beamline, partial fluorescence yield with a silicon drift detector over phosphor, sulfur, and boron and chlorine element, and is therefore quite well suited as a beamline for a combination of different important scientific discipline for the Canadian light source. Next slide. I'm talking now about a few examples specifically for the agriculture study. So this study was about phosphorus speciation in soils. It was a study that was performed using VLS PGM as well as SXRMB for collecting the phosphor K edge. And also we had some data from the infrared beamline. So the combination of this gradient thin film technique with the spectroscopy technique give the idea of which plant available phosphor species are in soil. And that is very important to determine what kind of phosphor you actually have in your field. All the free method can distinguish between different type of phosphate. So we have that the infrared is more sensitive to distinguish between the inorganic and the organic. The K edge, that is historically what has always been used, have a lower detection limit, can do species identification and quantification. However, the L edge provide more information, especially for organic and polyphosphate. So in the graph in the middle of the slide are data collected at the L edge of phosphor around 140 electron volt, while on the right-hand side there is the K edge for phosphor collected above 2000 electron volt. So if we go to this next slide, there is another example on this time hepatite in bone char to improve again the phosphor deficient soils. So for this study, 3 different location, soil from different 3 different location were collected, and there were some X-ray absorption spectroscopy were collected to observe changes in the chemical speciation of phosphor during the pyrolysis of this bone meal. So depending from the area where the soil was collected and the material and the pyrolysis of the bone char, it was very important to determine if the bone char is a good good material to improve phosphor for phosphor deficient soil. And also is very important to say that the production of bone char require actually no extra chemicals for then extracting the phosphor from the bone. So another study to try to improve the amount of phosphor available for a plant, and also to try to get this phosphor from material that otherwise would be just considered as waste material. In the following slide, so I'm going to talk about a project that we start up during the Pan American Conference. So this is a collaboration between the Canadian light source and the Brazilian synchrotron. So the reasoning is again to help the secure global food security, provide also an opportunity to user of one facility to access complementary technique that are available on other facility. Now, the Sirius synchrotron is does not have a low energy beamline like VLS PGM to provide access for their user to study those low energy phosphor, sulfur, and boron element specifically for agriculture interest. So the MAPLE project, for a user that apply to the MAPLE project, they can apply for beam time at the Canadian light source under this specific project. The project will be reviewed by both CLS and AfLS scientists. The data, the sample will be mailed to the Canadian light source, and we will take care of collecting the data for the Brazilian user, while, and this is very important, there will be support for data analysis from both the facility. We found that sometimes, especially for a new user or new technique, they have a very good set of data, but then they kind of get a little lost on the analysis of the data. So we would like also to provide some support for data analysis and then eventually data interpretation. So I'm very happy because the first paper came out and was a paper about magnesium enriched poultry manure to again enhance the phosphor availability in biochars. Then if we move to the following slide, what we are doing from the beamline point of view. So as I said, we have two types of detector, a multi-channel plate detector for total fluorescence, and this one covers the whole energy range of the beamline. And we have quite recently finished commissioning a silicon drift detector for partial fluorescence yield. And once we did the commissioning, etc., then I contacted a professor at the soil science department, so Professor Derek Pick, and I asked him if he had any sample that we could use to see how good the detector was for this type of study. So here there are the results from real sample from Professor Derek Pick, as well as Professor Enzo Lombi from the University of South Australia. On the left-hand side, you can see the total fluorescence recorded usually with a multi-channel plate detector, where there is a very annoying background that is very, very difficult to be subtracted. On the right-hand side, we have the same sample but recorded with a silicon drift detector where you can see the data are pretty good even without the need of any background subtraction. And with the silicon drift detector, we can have a proper normalization that also facilitate for combination fitting for better interpretation of what kind of phosphor are actually in the sample. Next slide. So something moving to boron, we did some study on boron in plant and in soil. For a plant, we were using some soybean plant, and the amount of boron from 3 different points of the plant, so from the nodule, the leaf, and the root were collected and are plotted on the middle plot, while on the right hand side there are some again a test result of boron from soil recorded with both the detector to understand how good the detector is, and especially how good is not just from a technical point of view but specifically for agriculture user point of view. That is sometimes the challenging part. So next slide. The other things that we are trying to commission are micron image capability. So we did again with some poultry litter that Derek Peak brought to the beamline. So you can imagine we have a distance station that is in a vacuum. Everything has to be below 10 to the negative 7, 10 to the negative 8 torr, and we load poultry litter, and that is the result. We did some imaging. We could select some different spots where there were a different amount of phosphor in, and then we did the same with a small leaf again, this time on the boron edge around 194 electron volt. So the results are very, very promising. We are very happy with what we are seeing. So the next slide, I believe, is something more, yes, an environmental point of view. So under environmental is a very, very big umbrella. You can do battery research under environmental. You can do tribology research under the environmental. But what we are seeing now that because the global demand of lithium is increasing, there is a need of a rapid development of the lithium resources. So we started to see geology coming to the beamline to actually do lithium, not for necessary for right away for as a battery or energy material, but just to see how the different rocks have a component of lithium, and if it's possible to differentiate the different lithium bonding in lithium-bearing minerals. So we did this study, and that was published with several lithium-bearing minerals. We proved that yes, it's possible to determine what kind of lithium, and so to determine also how then use this one as a possible resources for the request of the increasing request of lithium. Next slide. Okay, CLS and LAMP. CLS has been a partner in the LAMP project for several years. Just recently with the FAST team in 2023, Professor Kayla Hidalgo, and I'm very sorry that she didn't give her talk just before me, because it would have been a very interesting ending. She came, she spent 2 months at the Canadian Light Source. Originally,
She is here.
Okay. Good. So
she is here. So yeah, so she will follow you.
Yes, I'm not going to say anything. However, the project initially was supposed to cover to use 2 beamlines. We were able to chip in with the beam time from 5 different beamlines. It was a fantastic project. You can see there then the picture that we took at the end of this 2 months. And I really hope that we will be able to host Professor Alassane very soon. We are waiting for him to have all the paperwork ready, and we are very interested in what also he can do with this CLS and LAMP collaboration. So as a last slide, I believe I want to thank you everybody. I want, well, first of all, you for inviting me, all the users that have been coming with this unusual kind of a sample for a beamline that works at such a low energy. And of course, you for bearing with me this presentation that didn't work out as I was hoping. So thank you again.
Thank you for a very nice talk. It's very interesting. I'm actually very interested in these topics of an application. And
yeah, those are applications that are coming stronger and stronger, and they start to use also beamline that that have never been used. I mean, the first time that they came with soil or something, and I was, guys, I work in vacuum, but no, we managed to get it done, and we are getting a very positive result.
Yeah. So that's great, and we have to look forward to the next pulsar. And we have
Indeed,
to make it
and it will
global.
be again. We are going. The Canadian Light Source is going to organize the next one. It will be in 2025. So yeah, July was the one at Chess. So now is again our turn, and we are really ready to organize it.
Right. Well, let us know what can help. The African Light Source can help, and we'll try to get people to come.
Yeah, exactly.
Apply early to get the visas. I don't know if it's hard to get a visa.
That is a very huge problem, and I have to say that we have seen increasing problem for users that not necessarily just come from Africa, but also other countries. And it's not the first time we have a user that can't come, or rather than 2-3 people in a group, only one can come, and it start. We should work around this. We really need to find a solution. Yes. So Sekazi, we really need to find a solution.
For sure. We will. Yes. I have some ideas on that, on how to. It's a very hard problem, though.
Yeah. I also would like to point out that the Canadian Light Source has produced a number of excellent high school teacher workshops, and in a couple of them, LAMP has collaborated with them. So that's another thing that's going on with the CLS.
Yeah. And I believe that the CLS organize both for student as well as for teacher, for high school teacher workshop, so they can start already to bring up the next generation of scientists already from the high school. So very important. Very important. Yeah, thank you.
All right, thank you. So Kayla, welcome back. Let me see, you can share your screen, or do I have your presentation?
Thank you. Thank you for the opportunity. And I'm so glad to see Dr. Sekasi and Dr. Lucian from CLS. Sorry for the delay because I have another hour in Puerto Rico. So this is my presentation. Can you hear me fine? That's fine?
Yeah.
It's perfect.
Yeah. Okay, I am Kayla Soto from the University of Puerto Rico. I talk about phytoremediation using mangrove, an iron-based nanomaterial for contaminated environments. This is my graduate student, Dinora Martinez. She's from chemical analytical chemical from University of Puerto Rico. We are from Puerto Rico. This is a tropical island very close to Dominican Republic in the Caribbean. Very close to Haiti and Jamaica and Cuba. So this is the site map of highly contaminated sites in Puerto Rico. We have many problems with contaminated sites from anthropogenic factor like landfill and something happens with industry. And this is the area that have the most contaminated sites classified by Environmental Protection Agency as Superfund sites. What is the problem with this site? Is very close to the wetland and mangrove forest in Puerto Rico. So in our lab, we working with different heavy metal like mercury, arsenic, cadmium, and lead. In this case, I show all the result that we have with cadmium. What is important to working and especially with this heavy metal because they are human carcinogen. So the plan is working with phytonano-remediation using iron nanomaterial, mangrove plants for wetland decontamination process and use the remediation product for new material in green synthesis. So I working with nanomaterial because the nanoparticle have a small size, have a high specific surface area, and all nanomaterials are more reactive than granular material used in conventional treatment when you try to discontaminate many sites. So in my case, I work in a special with nanoparticle based on iron because iron is an essential micronutrient for plants, for human, and that's involved in different metabolism process like respiration, photosynthesis. That's present in different kind of food that we eat. So this is the synthesis of zero valent iron nanoparticle. I use iron chloride and sodium borohydrate to reduce a specific the iron to 0 valent. This is a synthesis very, very easy. So in this slide, you can see the letter A, the high resolution 10 image. This is a fresh nanoparticle. After synthesis, you can see the shell and the coal. The shell is iron oxide of like this, and a special hematite. And the image B is the nanoparticle after remediation process in contact with cadmium. So you see in this image, the change in morphology to form nanofiber. So that's very interesting because we have published that show that when you can use nanoparticle in contact with cadmium solution, you see a different morphology in the structure. So the question is, what happens when the nanoparticle is in contact with cadmium solution? In this case, I use an X-ray photoelectron spectrum, and this is very interesting because the nanoparticle absorb in the surface the cadmium ions, but have another chemical reaction. For example, reduction cadmium and form cadmium ferrite. So the other question is, what happens if I the opportunity to get the remediation product after the contamination process? So, and I use an Oriel quantum efficiency to try to understand what happened. I use this remediation product for photoelectrochemical solar cell. So the good result that we have is when I use this remediation product in FTO film, we can use for photoelectrochemical solar cell, because when I see in my result, I try to understand what happened only with the nanoparticle after synthesis. So you see in this graph, the red one, the nanoparticle after synthesis no have absorption of light. In case of the nanoparticle after remediation process in contact with cadmium, they change the morphology and absorb UV light, and in special 30, 20 to 30, 50 wavelength. So this is another application after remediation process that we have with this nanoparticle. So the question is, okay, this nanoparticle working with heavy contamination, but what happened if I combine this nanoparticle with mangrove? Because the mangrove have the capacity to remove different heavy metals in contaminated sites. Because these plants have a green technology, they can to do phytostabilization, phytodegradation, phytoextraction, phytovolatilization, and translocation. So in Puerto Rico, we can try to use a special mangrove from Piñones State Forest. This area is very close to touristic zone in Puerto Rico, so people fishing, people use for different entertainment the water to domestic and something like that. So I work in this area to sampling soils and water to see what happened with the contamination. So I try to simulate the wetland condition in my lab. So I work in special with 2 mangrove, but in Puerto Rico we have 4 mangroves: Rhizophora mangle, Avicennia germina, Lacunluria racemora, and Pterocarpus. So I work in special with 2 mangrove. Red mangrove, this is the common name, and black mangrove. Why? Because they are very close to the coast. So in Puerto Rico, it's an island tropical, and we have many areas with coast. So these mangroves have considerable resilience to fluctuation in sea level. So that's very important for the climate change. So the mangrove have many ecosystem services like coastal protection, water filtration, climate regulation. So in my lab, I have 2 chambers. One of them is for simulate what happened in water and soil with red mangrove, and especially in contact with cadmium solution. And the other chamber is for black mangrove to see what happened with the lead. So that's very interesting because I try to simulate the condition of the wetland in humidity, temperature, and the contamination. So the results that we have are very excellent results, because when this kind of mangrove, the black mangrove, have in contact with lead, with cadmium, with arsenic, contaminated site, and when I put very close to the root, one concentration of nanoparticle based on iron, we have better translocation of cadmium and lead from to the root to the stem and leaf. So in Canadian light source, thanks for the lamp, I passed 2 months working in what happened, and especially with this kind of mangrove when they are contact with this kind of heavy metal. So I have biosaks imaging, and that's very interesting because, for example, in the root, when I put this kind of mangrove, high concentration like 100 ppm with nanoparticle zero valent, we see a low concentration of calcium. Why? Because the calcium and cadmium compete for integrate in the vascular system and the plant. In this case, I see one shoulder very close to the calcium because there are competition all the time for a specific absorb this micronutrient that the plant needs. So in our study, I try to understand what happened when the plant is only contact with cadmium solution without nanoparticles. So that's very interesting because I see the increase in calcium, but not in cadmium. So that's the question is what happened only with the plant. The plants, we cannot, they have the capacity to absorb the cadmium to adapt a contaminated site. So they need the nanoparticle to more efficiently translocation process. So this is the other bit line that we use in Canadian light source, the BitMe. So that's very interesting because I have the leaf contour and the leaf of the mangrove contact with 100 ppm with nanoparticle close to the roots, and you can see many crystal forms, and especially in the leaf contour. That's very interesting because it's probably that this calcium oxalate. Why? Because when I try to understand what happened with calcium and cadmium in contaminated site, low concentration of calcium may increase cadmium uptake into the whole plants. So that can you hear me? Hello, can you hear me?
Yes, I
Yeah.
can hear
But we
you.
lost your share screen.
Oh, let me see. Let me try to. So how many time that we have?
You have 1 minute actually.
Okay, don't worry. So I talk only in the okay. Yeah, I try some. I have how many problem with the connection in Puerto Rico. So the process that we obtain in this in Canadian light source, we have a good result, an excellent result, because I try to understand what happened with this kind of mangrove in contact with lead and the cadmium. So in conclusion, I try to see what happened, and the result is a good result because we have better translocation of this heavy metal from roots to the leaf using a specific concentration similar to the wetland. So that is the presentation. I thank you so much for the LAM to this opportunity to working in the Canadian light source, and all the personnel, the scientists in the Canadian light source that help us with this project. So I don't know if you have a question. Thank you so much.
All right, thank you. Lucia, you have a question for the speaker? Well, that's a clap.
No, but I mean, I know that when Kayla came at the CLS, she and her student, they work, they really work a lot. They spend 2 months using 5 different beamline, analyzing the data, because as I said, it's very important that the user is then able to extract the information that they really need. And so I just, they did a fantastic job. So thank you.
Thanks. So, Caleb, let me ask you just a really quick question. Oh, let me check the chat first. Right. Have you taken samples from Vieques and seen what contaminations are left from Vieques' former reality?
Yes, I have another colleague that work in Vieques. So Vieques have many area contaminated with heavy metals, different kinds of uranium and another from like bomb different part. So yes, we have many sites similar to Vieques, because I start my story with an special Cataño. Cataño is another town that received many sources from landfill. And now I working with Piñones. What is the problem with Puerto Rico? Many people use the water from this kind of area, many people fishing. So that's a big problem that we have. And the other problem that contaminated this size is we have 60% of population that use septic tanks. So that's wastewater go to the different part of the Puerto Rico water body. So
okay, thanks.
thank you.
What do you think about the could there be a light source in the space where Arecibo used to be, the telescope used to be?
Yeah, I think that's probably the only problem that we have is with the electricity system. We have one company that try to recover the problem with electricity in Puerto Rico. That's the most difficult part. And the other is the maintenance. So that's the this is a great challenge that we have, but yeah, I think that's a good opportunity for us, and especially in the Arecibo Observatory.
Right.
Yeah, we do have a small movement that's growing to try to bring a light source to a synchrotron light source to Puerto Rico. But I suspect it won't be where Arecibo is located because it's not located in a good location. So what we're going to do is to try to do some studies of various terrains there and try to see where would be appropriate in Puerto Rico to site a light source. So that's definitely on the agenda. And I'd also like to thank Kayla for her excellent presentation and point out that she and Alessani and also Celine, 3 of our LAMP awardees, are actually participating in this program. Thank you very much.
Thank you for the opportunity. Thank you. That's a great conference.
Well, thank you. So I think, where are we now on the program? I think this was the last talk. Is that correct?
Yeah.
Well, thank you, everyone. So the conference resumes tomorrow. There are in the GMT +2 session morning, there's sessions of the African Physical Society that I think tomorrow is a condensed matter day. So you can look on the schedule. If you go to the website, you can look on the schedule and look at that. And then tomorrow afternoon, the AfLS conference resumes, and part of the first session, or I guess the entire first session, is about the Caribbean light source. So I hope you can join us there. Simon, do you want to, Philip?
I just think it's been a wonderful session, and thanks to all the speakers. And it's great to see alumni of LAMP. I really enjoyed that. And I really enjoyed the environmental aspect of the talks today. So thank you to everyone who participated. Thank you to the audience.
Okay. All right, well, we'll see you guys, excuse me, tomorrow afternoon.
Yeah.
Thanks, folks. Have a good evening. Bye.
All right.
Bye.
Cheers.